Zhang, who are the other co-chairs?
Rainfall from University of Connecticut and Samantha Stevenson from University of California, Santa Barbara.
Okay, thank you. I'll make them co-hosts.
Ute, do you want to try now? We can see you in the participant list. Oh, looks like we still cannot hear you. We see your audio is active, but we cannot hear you. No. Yeah, that's weird. Could you please try to switch to other like microphone on your computer?
Stop sharing for a moment. John, I have the phone number and the password for the phone dial-in, so she could do audio only, but we could do that as well.
Okay.
I think she left again. This is the information here.
The speaker will be from Germany. So this should work, right? The audio, the phone number.
Oh, is there a German number? Let me take a look. Okay, so that's the number for Germany. Same other information.
Okay. So maybe I can email the speaker.
That's it all in one.
Okay.
Good morning, Jean. Good morning, everyone.
Good morning.
Good morning. Looks like we are having a problem. The first speaker, Uta,
Yeah,
we cannot hear her, so I think she disconnected and wanted to try again.
well, if all else fails, you can just switch the order of the number. Switch her with Takasumi or Thomas.
Okay, that's a
Since
good
they're-
idea.
Though then you won't get the overview, but
So Uta joined the call very early and we tested, it didn't work. And I emailed her the phone dial-in number. If she can, I let her know that if she can join using her phone, then we could forward her slides. That's another
Okay.
option.
yeah, someone yesterday in one of the other meetings had to make hers a PDF because she had trouble with the PowerPoint. So they
Okay.
switched the order, I know. People are coming on now. Good morning, Alex. I see your face. Everybody else is still in hiding. Oh, and there's Matthias.
Hey, Jang, so you said they can't hear? They can see everybody and join the meeting?
What people can't hear, I can hear.
No, the
Yeah.
speaker.
I think the technical problem is only with Uta, the first speaker. Uta Merkel.
Okay. Yeah, try if you're talking to them, see if in the bottom left on Zoom,
Mhm.
they should be able to click the join audio and then make sure their computer volume is turned up. So if the bottom left doesn't say mute and it says join audio, then they should click that.
Mhm.
But that's the only thing I can think of off the top of my head.
They had joined audio because they were muting and unmuting, but we still weren't able to hear them. So
Okay, and they
it could
still
have been a
couldn't
problem
hear.
with their mic.
I
Yeah,
see.
you can change if you just do the up button, you can change what microphone, what speaker. You can also, yeah, switch to phone audio, audio settings, at least on my Mac, Zoom. So,
Mhm.
Okay, I see Uta again.
huh,
Hi,
good.
Young. Can you hear me now?
Yeah, great. Yeah, it's very clear.
Ah, perfect.
Okay, it's 8:30 now. Maybe we get started. Todd, if you please stop sharing. I have an intro slide. Okay. Okay, good morning, everyone. I'm Jiang Zhu, together with co-chairs Samantha Stevenson and Rainfall. will welcome you to the 2022 CESM Workshop Paleoclimate Working Group meeting. So today we have, before we get started, I want to remind people the code of conduct shown on the left. So by joining this meeting, you agree to follow the code of conduct. Please offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. Today we have 13 exciting talks in the morning. And for each talk, we will have 15 minutes in total, including Q&A, except for the first talk, which will be 20 minutes. Thank you, Ute, for agreeing to providing us an overview of the Palmetto project. And for each speaker, you will receive a reminder when there's 2 minutes left. And we will have 2 breaks for this morning at 10:25 a.m. and 12:10 p.m. After the second break, please come back for a general discussion and then a special discussion on the CSL proposal. Also, please email Elizabeth your slides after the workshop if you want them to be posted on the meeting webpage. So that's about it from me. I will stop screen sharing and I will handle the virtual floor to Rainfall, who will chair the first session for this morning. Ran?
Thanks, John. Thanks everyone for participating. So we have a set of 7 talks during the first session. I will give everybody a note when you have a 2 minutes left. If we have more questions after each of the talk, please save them for the general discussion, or you can ask them in the chat. All right, our first talk is given by Ute Merkel. The first 3 talks are going to be on Palmetto initiative. Feel free to share the screen and begin.
Hello, everyone. Can you see my slides?
Yes, we can see them.
Thank you, Betty, for letting me know. I'm just trying to get to the presentation mode. No, here it is. Yeah, so I hope everything is fine. I'm sorry for not switching on the camera. I have some technical troubles right now. I'm sorry for that. Can you nicely hear me?
Sounds good.
We can hear you.
Okay, thank you very much. Okay, so thank you very much for inviting me to give an introduction to the Palmetto initiative at this meeting. Thank you to the organizers of this workshop. So I would like to introduce you to the Palmetto initiative, which is a German climate modeling initiative. My name is Ute Merkel. I'm working at MARUM, the Center for Marine Environmental Sciences at Bremen University in Germany. And the long title of Palmetto is From the Last Interglacial to the Anthropocene, Modeling a Complete Glacial Cycle. The coordinators of this project are Mujib Latif from GeoMar in Kiel and Tatjana Iljina from MPI for Meteorology in Hamburg and Michael Schulz from MARUM in Bremen. Palmetto is currently in its second phase, and if everything runs fine, the jury is still out, then the entire duration of the project will be for 10 years. And Palmetto is a contribution to the Research for Sustainability Framework Program of the German Federal Ministry for Education and Research, and it involves universities, Max Planck Institutes, and research institutions of the Leibniz and Helmholtz associations. And the total budget for Palmetto phases 1 and 2 is about 34 million euro. about 36 million US dollars. And this allows to currently fund about 39 positions for PhD and postdocs. And all the institutes also provide additional contributions from their own budgets. The scientific objectives of Palmetto are to identify and quantify the relative contributions of the fundamental processes which determined the Earth's climate trajectory and variability during the last glacial cycle. And we are using comprehensive Earth system models to simulate the climate from the peak of the last interglacial up to the present. And that also includes looking at changes in the spectrum of variability. And a third focus is to assess possible future climate trajectories beyond the 21st century during the next millennia by using these sophisticated ESMs that we tested for the past. Palmetto is structured basically into 3 different working groups, and there's one working group focusing on the physical system, one on the biogeochemistry system, and one mainly focusing on data synthesis. There are also cross-cutting activities where the focus is on model coupling, runtime optimization, but there's also activities dealing with data management and with the comparison between the model results and proxy data. And we have one EMIC on board of this whole initiative. That's the Climb by X model, which is mainly developed at the Potsdam Institute, TIC, in the group of Andrzej Ganopolski. And Palmetto is, and along with this EMIC, we also, of course, have the 3 main ESMs on board, which are the ESM of the Alfred Wegener Institute in Bremerhaven and the Max Planck Institute in Hamburg, Max Planck Institute for Meteorology, and of course, which is of major interest for this meeting, the CESM 1.2 model that we are mainly using at Marum and Bremen. In the next couple of minutes in my talk, I will give you some introduction to my own work that I did as part of the Working Group 1, dealing with some aspects of marine isotope stage 3. And after my talk, you will hear 2 more Palmetto talks, which are given by Takazumi Kurahashi Nakamura, whose work is from Working Group 2, dealing with the marine carbon cycle. And afterwards, Tamas Kovac from Working Group 3, who presents some work with the isotope-enabled CESM 1.2 model from the forward modeling work package. So this brings me already to my scientific part, dealing with climate variability on centennial to millennial scales in CESM. And I think I don't have to make a long introduction why we are interested in this topic. So we all know that especially marine isotope stage 3 is characterized by very pronounced millennial scale oscillations and very rapid changes between cold stadial states and warm interstadial states. And of course, the question is what controls the occurrence of these oscillations. And one candidate has been mentioned already quite early, for example, in this paper by Zima et al., which mentions the ice volume as a potential candidate. And they showed with an ocean box model and a 1D ice sheet model that whenever the modeled ice volume is in a window of intermediate ice volume, then the ocean model produces something like Dansgaard-Oeschger-like events. So switches between a cold mode and a warm mode. And so something like Dansgaard-Oeschger variability along with intermediate ice sheet volume. And more recently, there has also, for example, been a paper by Vettoretti et al., where they are talking about the role of CO2 in determining self-sustained climate oscillations, which can appear spontaneously within a CO2 window of about 190 to 225 ppm. So there are several candidates out there which may play an important role for determining millennial scale variability. And one of our Palmetto exercises is to test boundary conditions which may contribute to the Dansgaard-Oeschger window, which may make up the window. And one of our mini model intercomparison projects within Palmot is to explore the parameter space and use different combinations of greenhouse gases and ice sheets. Here we focus on those of the time slices for 21 and 38K to capture mostly the upper and lower ends of the greenhouse gas range here on the left side, and some high and lower end ice sheet volume for marine isotope stage 3. And this whole exercise is done with CESM 1.2 using the comparatively high resolution setup, given the long simulations that we are going to do, and we run it at 2 degrees in the atmosphere and 1 degree in the ocean. And the simulations are done at H11 in Berlin and Göttingen. So to summarize, we have a set of experiments where we use different combinations for ice sheet, greenhouse gases, and orbit from 21 and 38K, and try to identify the relative role of these individual boundary conditions. One of the first results, for example, if we look at the Atlantic Meridional overturning circulation in the simulations, is that we get a reduction of the AMOC compared to pre-industrial levels, and on top of that lowering of the AMOC strength, we also get some centennial scale or multi-centennial scale oscillation at the LGM. If we leave everything at LGM conditions and just switch on the 38K ice sheet, then the model produces a millennial oscillation, which actually is at Dansgaard-Oeschger timescale. So the period is about 1,500 years in the simulation. If we look at the simulations, which all have the higher 38K greenhouse gas concentrations, such oscillatory behavior is not evident, and it seems that the model rather stabilizes or equilibrates in these simulations. We also get a weakening compared to pre-industrial levels, but still the AMOC strength is higher than in the LGM simulation. And this can also be seen here, for example, in a latitude depth section of the Atlantic Meridional overturning circulation. We see that for the classical LGM conditions, we get some, we see the North Atlantic deep water cell and the Antarctic bottom water cell. And if we go to the simulation where the LGM conditions are maintained, but we just go to the 38K greenhouse gas concentrations, then there is a strengthening and also a deepening of the North Atlantic deep water cell, whereas the Antarctic bottom water cell is hardly changed when comparing these two simulations, which only differ in the greenhouse gas concentrations. So the main message from, or the most interesting aspect of these simulations is, we think, of course, this millennial scale oscillatory behavior. So we also see something which has been postulated by the simple models quite some time ago. And in the remainder of my talk, I will mainly focus on the simulation, which shows this oscillatory behavior on millennial timescales. So if we look a bit more closely into those results, we see, for example, that Greenland temperature shows in the simulation periods with quite some drastic increase of surface temperature, and then a gradual decrease or cooling of temperature. And compared to that, the temperature fluctuations over Antarctica are comparatively moderate, and the main point also is that a gradual warming over Antarctica is then followed by a rapid warming over Greenland. And this somehow, without making any causal arguments at this point yet, this nicely fits the bipolar seesaw concept. So the temperature changes in these millennial scale oscillations are quite large over Greenland. So it's more than 10 degrees within a comparatively short period of time. But it nicely fits to what has been reconstructed from the N-grip temperature ice core reconstruction, for example, by Kindler et al., where they find that during marine isotope stage 3, the temperature changes can actually be quite large, on the order of 5 to 15 degrees Celsius within a relative short period of time. So the model seems to capture this amplitude quite well. Another interesting feature is that these millennial scale Greenland temperature fluctuations seem to operate in concert with AMOC variations. So whenever there is a drastic increase in Greenland temperature, then there is also a drastic strengthening of the AMOC, and then they weaken gradually and also in concert. If we look at the sea ice fluctuations, there are also some covariability, so that we have this blue shows the time evolution of the sea ice area in the Arctic, and whenever the Arctic sea ice shows a drastic decrease, that goes along with a drastic increase of the AMOC. Antarctic sea ice also shows some millennial scale fluctuations, but there's also some kind of plateau behavior in between, which definitely needs to be explored in more detail. When we do some kind of composite analysis across these high and low AMOC states, then we see, for example, that during the high AMOC phases, which can be compared to some interstadial state, we have quite some strong North Atlantic deep water cell. And in contrast, the low AMOC states compared to a stadial state maybe shows a clearly stronger Antarctic bottom water cell and a very pronounced weakening of the AMOC compared to the interstadial state. Matthias Prange has already started to look a bit more closely into the multi-centennial mode that we find at the LGM. He looked at, so that was what I mentioned already earlier, that we find some moderate AMOC variability on these multi-centennial timescales under LGM conditions. And what Matthias found so far is that there is quite some nice covariability as well between AMOC and Greenland surface air temperatures, and some anti-correlation to the Arctic sea ice area on these timescales. And when digging a bit more into depth regarding the mechanisms, he found that there is quite an important role of freshwater transports, which are operating in this centennial mode, and which nicely showed that that there is some back and forth between strong and weak AMOC along with the freshwater transports in the North Atlantic, and that the freshening may lead to impacts on the convection or the northward salt fluxes, or the advective salt leads to freshening in the North Atlantic convection sites, which in the end may increase, may weaken the AMOC, and then in turn close the loop again and lead to a reversal of the phase. So with this, I would like to already come to my conclusions and some outlook. So I presented you some first results from the CESM 1.2 experiments we did in Palmetto. And we do this exercise to explore the parameter space for AMOC variability based on 21 and 38K boundary conditions. These simulations show that there is some multi-centennial AMOC variability under LGM conditions, which may be subject also as well to the role of continental ice sheets. It seems that our CESM 1.2 simulations confirm the existence of a Dansgaard-Oeschger window with respect to the intermediate ice sheet height. So the mechanisms behind that still need to be explored a bit more in detail. But at least it's already quite interesting that the millennial scale climate oscillations we get in these simulations show a similar Greenland temperature range as the NGRID record. We see from these simulations that the AMOC and Greenland temperature are fluctuating in concert. It seems that sea ice may play an important role in this context. So preliminary results show that that for the high and the low AMOC phases in these millennial scale oscillations, the convection sites shift quite drastically along with the sea ice distribution in these simulations, and we're currently looking a bit more in detail into that. So there are MIP efforts going on within Palmetto, so we will further explore the differences between the different Earth system models involved in Palmetto and hopefully get some more insights into the relative roles of CO2 and the ice sheets from these simulations, and may also learn quite something from model dependencies or the different sensitivities of the different Earth system models involved in Palmetto. And with this, I would like to thank you for your attention.
Thanks, Ute, for the wonderful talk. We do have a few minutes for a few questions. If you have a question, please raise your hand on the Zoom screen so I can see that. Fanny.
Hi, thank you for the great talk. And I was just wondering if you have any idea what kind of feedback mechanism is going on with the sea ice and the temperature and so on. So it really looks like there. So what is you mentioned that you will look into it in detail, but do you have any idea what's going on?
At the moment, I only can hypothesize, so I cannot give a definite answer yet. But what we definitely will have to look at is also the deep ocean. So from simpler models, there has been proposed also a deep decoupling mechanism, so which also involves the deep ocean. So I think on these long time scales, it definitely is not just the interaction between ocean surface and the atmosphere, but we really need to get processes into play which have the long memory and which really make up for the timescales of more than 1,000 years.
Okay, thank you. Looking forward to what you find out.
Thank you.
Any more questions? Actually, I have a question. What I was wondering, so you mentioned that the simulations are initialized with 21 Ka state, and when you prescribe the 38 Ka ice sheet, you get this a very super interesting sawtooth behavior of the AMOC and the Greenland temperature. I was wondering, does that also have something to do with how you initialize the run? Let's say if you initialize with 38 Ka equilibrium run and prescribe 38 Ka ice sheet, would you also get the same oscillation condition?
That's an interesting question, which would require quite some additional computational efforts to really test that. At this point, all these simulations have been started from exactly the same initial state. So in that respect, we cannot say anything about whether the initialization would make a difference. So it's just that we can compare this set of experiments and know that they all have been initialized from the same state.
Right. Thank you.
But you're definitely right. It would be very interesting and worth to look more into that to see how different initial states might have an impact. And if I remember correctly, then that Matthias Prange looked more closely into different initial states for the LGM, and there it may actually have an impact on what oscillatory behavior you actually get.
Okay, thank you. Right, I think we should move to our next talk. Yeah, if you have more questions, feel free to save them to the chat or ask later. Thanks so much for the great talk, Ute. Our next speaker is Takasumi Nakamori, who is also going to talk about Palmetto initiative. Great, we can see your screen.
Yes, great.
Yeah, I can hear you as well.
Yeah, also nice. So I'd like to say a big thank you for invitation. I really appreciate this nice opportunity. As Ute quickly introduced, I belong to the working group 2 of the Palmetto project, which is taking in charge of the biogeochemical part of the project. So in the framework of the project, recently we made some time slice simulations aiming at MIS3. And today I will introduce some results from the recent work. So I start with some introduction about marine isotope stage or MIS3. And MIS3 is characterized. MIS3 is a intermediate glacial conditions, which is characterized the remarkable linear scale variability of a climate. And this figure is taken from the paper by Ahn and Brook 2014, showing the time series of Greenlandic temperature and CO2 level in the atmosphere, and the temperature in the Antarctic regions as well, from for the time window from the 22 Ka to 40 Ka, and so this small window is overlapping. So they suggested that there are 2 kinds of stadia. So one is a long one shown in this pink color, and which is accompanied by the Heinrich event. And the other one is short one is shown in this light blue color, which is not accompanied by the Heinrich event. And they found so another characteristic of the 2 different types of stadias in the long one with Heinrich event. So in the long one, there was a remarkable increase of CO2 level in the atmosphere like this. But on the other hand, in the short stadias, there were only minor change of CO2 level like this, except for the very long time scale decreasing trend. But in this study, so we'd like to suggest actually there is another difference between the 2 these pink stadials, between this stadia and this stadia, and that is the flux of aerian dust into the Antarctic region. This is a time series of a proxy of aerian dust flux into the Antarctic regions during the past. And actually, between the 2 stadia time windows, actually there was a very highly remarkable difference in dust flux into the Antarctic regions. So for 38 Ka for the earlier one, the dust flux level is as low as the modern level. On the other hand, for 29 Ka, the dust flux is as high as the LGM level. Please note that the vertical axis is in log scale, so the difference is really huge. Okay, so we'd like to suggest that there is another difference, one difference between these two long stadials, and that is the mineral aerial dust input into the Antarctic. So based on this observation, so in this study, we would like to suggest there are three types we can categorize. We'd like to suggest there are three types of stadials during MIS3, depending on the Heinrich event or not, and depending on the dust input. For example, in this type 1, so it is accompanied by the Heinrich event, and it has a low dust input from the atmosphere. And this motivated us to make 9 simulations in total, and 3 simulations for each time period, including 38 Ka, 29 Ka, and 21 Ka. And each of the 3 time slices, we gave 3 different freshwater forcing as a parameter study, and we studied the behaviors of the carbon cycle corresponding to the different physical state in these 9 simulations. As a tool, of course, we used CESM version 1.2, and we adopted a low resolution setting. The atmosphere had T31 resolution, and the ocean had nominally 3 degrees resolution. And we used interactive carbon cycle module with BEC. This interactive means, so we explicitly calculated the CO2 level in the atmosphere in the model, and that simulated CO2 level is actually used for the radiative forcing. So again, as I mentioned quickly, we made 9 simulations in total. So 3 simulations for 3 time periods, and actually we've done one more baseline simulation for the standard of the comparison. And all of them were started from a common initial state, and the initial state is given by another separate time slice LGM simulation. And for this LGM simulation, we drove the model by the forcing according to the PMIP4 protocol, and we tuned the ocean inventories, total inventories of carbon and alkalinity to satisfy the 190 ppm of the CO2 level in the atmosphere, and also to satisfy the estimated carbon storage in the deep ocean given by the study of Zantine et al. 2013. Then we changed the boundary condition suddenly. So we changed the ice sheet configuration according to RAC 1D reconstruction for each time period. And also we changed the orbital forcing according to the different times period. And as a parameter study, we gave a different amount of additional freshwater forcing onto the high latitude of North Atlantic to manipulate the ocean saturation, global ocean saturation. And for the dust forcing, we used the modern flux for the low dust input, and we used LGM dust input for the high dust condition to mimic them. So this is the overview of the simulated AMOC for all the simulations. So in this vertical axis, you see the different 3 time slices. And this, in this horizontal direction, you see the different additional freshwater forcing onto the North Atlantic. So in the baseline experiments, we've got this quite strong and deep AMOC structure like this. And as you expected, the more freshwater forcing onto the North Atlantic, we got the weaker AMOC like this. And this 38 Ka series and 21 Ka series had quite similar sensitivity or behaviors of AMOC, so responding to this additional fresh water. But this only 29 Ka had slightly different behaviors. Next, I show the simulated CO2 level in each experiment. These red numbers show observed CO2 level in the atmosphere taken from ice core data, which were the simulation targets. And in the baseline experiments, we successfully obtained 189 ppm, which was really close to this target value, thanks to the tuning of the ocean inventories of carbon and alkalinity. And one important result is that tuning, the same tuning also worked quite well for the other simulations. Yeah, so each series of simulations roughly capture the each of the target values like this, and the simulated CO2 level somewhat depended on the AMOC strengths or on the global mean SSD, because there were the anti-correlation between this AMOC strengths and the global mean SSD. And there was much stronger dependency on the dust input, which is showed by the contrast between this series and this series. And in the next 2 slides,
2 minutes.
I will.
Sorry.
Okay.
Sorry, you have 2 minutes left.
Okay. Yeah, in the next 2 slides, I will discuss the processes in the simulations. First one, I show the effect of dust input. The dust input is, in short, the ion fertilization effect to strengthen the biological pump to draw down the CO2 level. So for that comparison, I picked up the 2 simulations, one from 38 Ka and one from 29 Ka, which have very similar AMOC structure like this, but a different CO2 level. And with high dust input in Antarctic region in this experiment, so this is the carbon storage in the Atlantic section. So there was a much stronger biological pump, mainly in the Southern Ocean, to transport much more CO2 carbon into deep ocean like this to the greater storage carbon in deep ocean. So the CO2 level it decreased due to this enhanced biological pump, also induced feedback from SSD changes. And this scenario is also supported by the remarkable greater consumption of macronutrients at the surface, shown as you see here. The next one is I discussed the effects of the freshwater input. The freshwater input has two effects. So one effect is change the SST distribution, and the other one is more stagnant deep water for more efficient carbon storage. But in total, and the effect of SST change is slightly higher than this, the more efficient storage of carbon by the stagnant water. So the global mean SST is slightly higher here than this, and that's why we got a slightly higher CO2 level like this. This is a kind of summary diagram showing the temperature, showing the relationship between the temperature change in the Antarctic region in the one downscaled earth sugar event, and the CO2 change, CO2 level change also in the same downscaled, the same event. And this circles show the result of our study, this study, and the triangles show the observation data taken from ice core data. And our simulations roughly captured the difference grouping of the three different types of stadia as a whole, although it was a little bit exaggerated due to the mismatch of model data mismatch mainly in this type 1. And it is comparatively more difficult to distinguish the type 2 and 3, at least in this diagram, because these two types overlap each other to a substantial degree. So now this is the conclusion of the study. So we made some idealized simulations for MIS3 to discuss the behavior of the carbon cycle. And the simulations captured roughly, the simulations show the potential to capture the characteristics of the three different types of MIS3 stadias. And again, the one important result is the ocean inventories of carbon and alkalinity tuned for the LGM also works for the other time slices in MIS3. And unfortunately, we did not find conclusive differences between type 2 and 3, at least in the framework of the study. And possibly the freshwater perturbation of a different magnitude might be explain the difference, but the relationship between the lengths of time lengths of stadias and the amount of freshwater input should be further examined to answer to this question specifically. So this is the end of the talk. Thank you very much.
Thanks so much, Takazumi. Unfortunately, we're out of time, so I'm going to move to the next talk. If you have any questions, feel free to ask in the chat. Okay, our next talk is going to be given by Tomáš Kovič. Tomáš, please share your screen and we can begin.
Yeah, can you hear everything all right?
Yes.
Yeah. Excellent, thank you very much. All right. So welcome to the third and then last Palmetto-related talk. The following slides were presented in a project meeting about a month ago by my colleague, Martin Werner. Now, unfortunately, he is busy today and cannot make it, but instead I'm very happy to be here and present some of our results from people listed here from the Alfred Wegener Institute and at Marum, the University of Bremen. Now, what I will present here today luckily, Ute has already showed this structure of PAMODs. I don't need to go too deep into it. I'm going to present results of the working group 3, or specifically 3.3 over here. The focus of this group is an integrative forward proxy modeling with the aim to bridge the gap between data assembled and models used within PAMOD. The goal is to enable a quantitative and process-oriented model proxy comparison, linking modeling efforts performed within the working group 1 with data synthesis provided by the working group 3 other subprojects, and also the tools and concepts for model data comparison provided by the cross-cutting activities. A key question in PAMOD is how much climate variability depends on the mean climate state, and also whether our models can simulate it correctly. Of course, capturing the mean climate is very important also for the past and the future, but so is the range of climate variability. And also as an outlook, if the models can do that in the past, then what can we expect from the future, how it looks like, and what can we learn from that? For studying climate variability, we're using the data compilation product, PAMOD 130K, assembled by our colleagues Lucas Jonkers et al. Within PAMOD. Here you can see a map of data coverage for oxygen 18 records from marine sediments within this product. And we're also using a first long transient simulation within PAMOD, a low resolution MPISM simulation with prescribed ice sheets from our colleagues in Hamburg. If you look at the spectrum here, this is what a true climate spectrum would be. This is power density versus frequency. And what we can actually observe in proxies is the blue line. It's different because, so that's the observed proxy spectrum, and it's different because, of course, there's noise from measurement error and data aliasing. Our colleagues, Andrew Dolman and Tom Lepple, came up with an estimated proxy spectrum that eliminates the effect of this noise. And they developed new autocorrelation function methods for gappy time series. And with this, for the first time, we can actually compare the true proxy spectrum to the spectrum of the simulated climate variability. And some results of these efforts are shown here for the Delta 18O of calcite in the ocean. And Andrew and Tom found that the climate variability is quite state dependent. So looking at the spectrum, the inferred climate spectrum in red, we see that this inferred climate is 2-3 times more variable in glacial time periods than in the Holocene. In terms of the models, we show here in green the PAMOD transient run with MPISM, and also the yellow is Trace 21K with CESM3 that I'm sure you all heard of. And what we can see here is that the PAMOD run gets the order of variability quite correctly for the transition and the glacial state. And that it produces at the same time a too stable climate in the Holocene, especially in the late Holocene. And it is also notable how this run, the green, is closer to the inferred climate variability than Trace 21 for the glacial. There's quite a difference for that. But at the same time, this is even more stable than that in the late Holocene. This is a really valuable study, but it still has one caveat, namely that this simulation with the MPISM has no isotopes in it. So we are just modeling the Delta 18O from temperature and salinity results based on a transfer function. And of course, the question is, how stable is that? Can we apply the same transfer function over time? And or it changes? And if yes, how does it change? We are trying to find answers for this with the use of isotope-enabled simulations. These are very valuable because they can directly simulate the isotopic composition of water in the entire hydrological cycle. And it's useful because this way we can use them to validate and calibrate the transfer function. Plus, of course, they can also provide a better data for model proxy comparison. Okay, so we are using two isotope-enabled fully coupled models in PAMOD, ICESM and AVESM. And we're looking mainly at Delta 18O in ocean water and precipitation for equilibrium, and also transient climate simulations. These simulations comprise different types for the deglaciation and also for the lost 6,000 years in terms of the transient runs. And we also have steady state time slice simulations that we have for warmer climates, for example, for the PI, different parts of the Holocene, also much further in the past, the last interglacial at 127 K, and also for glacial climates too, like last glacial maximum, and also the MIS3 at 38 K. Okay, so looking at some of these, some of the time slice simulations, we can see here that, for example, for the LGM minus PI sea surface temperature anomalies, the ICSM results are on the top, AVESM in the bottom. What we can see here is that ICSM simulates a much larger cooling than AVESM. That gets the global mean SST anomaly remarkably well if you compare it to the GLOMAP reconstruction recently produced within Palmetto. Looking at regional differences and comparing them to the temperature reconstructions, these are shown as these colored dots here. ICSM does a good job in simulating the North Atlantic cooling, but shows too much cooling at low and mid latitudes. That's where mostly this larger anomaly comes from. And also the Southern Ocean is too cold in ICSM. The anomaly is too large there. Something that's not uncommon for coupled model simulations. On the other hand, AVESM gets the low and mid latitudes much better, but shows too little North Atlantic cooling. Overall, looking at the regression slopes between reconstructed and simulated SST anomalies, the models, well, perform modest at best, suggesting many regional characteristics are not particularly well captured. That is why it is particularly interesting that if you compare the simulated delta oxygen 18 in calcite to the reconstructions, we get a much better agreement with the data. So for some reason, the models are able to produce a much better fit than for SST for both models. And so this kind of suggests that the conversion between oxygen 18 and SST for the data products or model analysis that we use might need a little bit more attention. Again, also in terms of the results, we see a bias in the Southern Ocean, a too large enrichment in this case, actually for both models, more so in ICSM. And also the models do not agree on the data 18 in the Arctic surface water. This is unfortunately a bit difficult to evaluate due to the lack of data points to compare there. In terms of delta 18 in precipitation, both models capture the stronger contrast between high and low latitudes for the LGM in comparison with the PI. This evidence, of course, for an enhanced polar terminus for precipitation, but this depleted anomaly is much more restricted to areas over continental ice sheets in AVESM, not as well spread over the entire Arctic, for example, than in ICESM. Another remarkable difference is a depleted bias over land in general in ICSM, a known bias for a coupled configuration of this model. If we compare the model results to the observations, the big picture looks really nice. So the regression fit is quite good, especially for ICSM. But unfortunately, looking more at different types of data, for example, neither models fit the low latitude data from speleothems well. These are these brownish triangles. So the fit is quite bad for those. But this is also a common problem for isotope models. For the Arctic ice cores, they're in blue. The AVESM does a much better job, a better fit, but it actually shows a too small depletion over and around Greenland. That's the purple squares here. Then ICSM that reproduces data in the Greenlandic ice cores significantly better. With ICSM, we also looked at MIS3 at 38 Ka. These are shown on the right-hand side compared to the LGM anomalies that I just showed on the left. The anomalies for MIS3 are somewhat weaker than for the LGM in terms of the delta 18 in precipitation, and the fit is somewhat worse too if you compare them to the observations, although the mean error is smaller. In the ocean surface waters, in the bottom, again, the anomalies in the northern North Atlantic seem to be quite close to reconstructed values. But for example, for the MIS3, another difference, we get a very much depleted Arctic Ocean. Again, this is a bit hard to assess because we do not have reliable data points there. But that's also one notable difference between these two climate states in the model simulation. As I showed in the beginning, the conversion between delta 18O and the temperature is important for the climate variability studies. And what we did is that we looked at the simulated conversion factors between surface temperature and delta 18O in precipitation for model grid points over Greenland, that's again in purple, and Antarctica in blue for different climate states. And what we have found is that our ICSM simulations suggest different slopes for the PI, LGM, and MIS3, especially over Greenland. So comparing these numbers here in purple, there's a better agreement for Antarctica, although still with some differences. And this is largely due to the fact of the changes in ocean surface, because we also ran the atmospheric component alone, ICAM, with prescribed surface boundary conditions, and we got a much better agreement between PI and LGM. That was a greater improvement for the Greenland regions, not so much for the Antarctica. So the differences in slopes from these simulations suggest that the isotope-based temperature reconstructions in Antarctica and Greenland require different conversion factors for different climate states, for glacial and interglacial climate states. However, if we make use of the fact that we have two isotope-enabled models in Palmetto and do the same analysis for RVESM, we get that the models do not agree. The relationship is much more stable for RVESM, and its slopes are actually also closer to the real ones inferred from ice core data for the pre-industrial, also for Greenland and Antarctica too. At the same time, if you remember, RVESM actually showed a worse fit for precipitation delta 18O, at least for Greenland, around Greenland, than in ICSM. So we're still working on this. It's still an open question how to reconcile this difference between the models.
2 minutes left.
Thank you. Finally, if we look as a little outlook, I'd like to give a bit of outlook also on the warm climate simulations. These are with RVESM for the late and early Holocene, and on the right side for the last interglacial at 127K. These are anomalies of delta 18 precipitation on the top and ocean water surface in the bottom. This is very much work in progress, but you can see that the model has potential in capturing the observed anomalies for warm climates too, even if it's far in the past, like for the last interglacial. There are quite a few data points, of course, from ice cores, but they produce their remarkably good fit, even in this warm climate state with ESM. I also mentioned the plant transient simulations before. These are currently being designed or tested. For example, with RVESM, they already completed a test run with acceleration for the complete deglaciation with water isotopes, with dynamic river routing, and also isotopes enabled in iceberg model with transient forcing, so orbital parameters, greenhouse gases, and a black one deglacier topography. There's still some questions to be figured out, like the precise application of isotopic meltwater fluxes. And also at the same time at Marum, we are preparing the transient runs for ICSM. Okay, so a few take-home messages in the end. Based on our climate variability studies, the glacial climate was much more variable than in the Holocene. And our transient simulations show realistic variability for the glacial and transient periods, but they appear to be too stable in the Holocene, especially in the late Holocene. The simulations show very good agreement of simulated surface water delta 18O anomaly for the LGM, and a fair to very good agreement of values in precipitation for the LGM and the late Holocene and the last interglacial. Our ICSM results suggest the different conversion factors for isotope-based reconstructions in Antarctica and Greenland for different climate states. At the same time, the RVESM results do not. Of course, the question here is why. So that's for future work again. Finally, our first transient isotope simulations are being either in progress or in planning now, and they will follow soon. So expect some exciting results about that too in the near future. yeah, with this, I would like to thank you for your attention, and I hope I left some time for a few questions.
Yeah, thanks, Tomasz. We have time for one quick question. John, go ahead.
I have one quick question. So do you have like sea ice cover reconstruction to constrain the Southern Ocean processes, especially the SST?
Yeah, so we did not look into that direction yet. That would be actually a good direction to go. So we do not use anything like that, neither in ICSM or RDSM.
Great, thank you so much, Tomasz, for the
Thank you.
wonderful talk. If you have more questions, feel free to ask them in the chat. Our next talk is going to be given by Fanny Kellerman. Fanny, feel free to share your screen and begin.
Hi, good morning, everyone. Do you see my slides? Yes.
Yeah.
Okay. So I'm Fanny Kellerman. I'm from the Goethe University in Frankfurt. And my topic is the partitioning of meridional heat transport in the early Eocene climatic optimum in deep model simulations. And I'm working in a project called FEVA with my colleagues. And this project is investigating past warm periods, which could be analogs for high CO2 future. So our motivation is to investigate the early Eocene climatic optimum, which was a very high CO2 climate. And proxy data had shown that the meridional gradient was weak and there was a polar amplification. And our initial question was if the meridional heat transport is a positive contributor to the polar amplification, or is it a negative contributor? And it is also known that the meridional heat transport is mainly determined by the Earth-Sun geometry and the mean albedo, and it is very quite insensitive to the structure of and the dynamics of the atmosphere-ocean system. Nevertheless, if we are partitioning the meridional heat transport into different processes, this helps us understand better that climate, what is happening there with the different processes. So that's what I'm doing. The data which I'm using for this analysis is from DeepMap, from the Deep Time Modeling Comparison Project. And I'm analyzing all simulations. And so far, these results are for CESM, Cosmos, and GFDL. And I will finish everything for all of the models, but the results which I'm presenting here, the plots will be from CESM, but the conclusions are those which true for all three models so far. So the method which I'm using is von Donohoe et al. 2020. It calculates the transport values from monthly mean model data, which is perfect for the deep data set. And first, the meridional heat transport is calculated, then it's divided into atmospheric heat transport and oceanic heat transport. And for now, I'm focusing on the atmospheric part, which is further divided into meridional overturning circulation, stationary eddies, and transient eddies. And all three of these can be divided into moist and dry transport. And if you look at the annual meridional heat transport, here you can see the three models which I choose now. The black lines representing the total meridional heat transport, the red ones, the atmosphere, and then the blue, the ocean. The solid lines are the control simulations, and then the dashed lines are the different paleo simulations. And if the value is positive, then it means northward transport. If it's negative, it means southward transferred. And what you can see is that indeed the meridional heat transport is similar in the different models and stable among the different CO2 values. And the contribution of the to the polar amplification from the models is not coherent. CSM contributes negatively, Cosmos positively, GFBL positively, so it's not a clear picture. And what we can also notice is that the atmosphere and the ocean transports compensate each other, so that in the end, the meridional heat transport is not changing so much because the atmosphere and the ocean compensate. And if one looks at the CO2 effect, so comparing the different Paleo simulations, different CO2 value Paleo simulations, one sees symmetric results or changes, and that the atmosphere transports more energy poleward, and the ocean transports less energy. And in the tropics, we see that the headley cell circulation is more intense, and that you can see here in this picture. The meridional overtonic circulation is plotted, and which is the dark blue line. But if you look at the moist and the dry part of the meridional overtonic circulation, which is the light blue and the yellow lines, you can see that the circulation in the tropics, so between 30 degrees and 0, is indeed increased in the higher CO2 simulations, which is the dashed lines. But in the end, the whole meridional overtonic circulation transport is not changing so much. In the subtropics, what is interesting is that we found an increase in poleward moist transport by stationary eddies, which means the monsoon systems. So on this figure, you can see the change in transport via stationary eddies between, in this time, the CSM 9 times CO2 and 1 times CO2 simulation. So these peaks here do you see my cursor? At the 30 degrees. And if we look into the non-CO2 effect, so if we compare the control simulation to the 1 time CO2 paleo simulation, so this means that we are comparing the effect of paleogeography, the changed vegetation, aerosols, and that there is no continental ice sheet in the paleo simulation, we see an asymmetric change. And then the southern hemisphere, the atmosphere transports less, the ocean more to the South Pole, and then the northern hemisphere the other way around, so the atmosphere transports more and the ocean less. And what I found very interesting is that at the mid-latitudes we find an increase in polar transport by transient eddies and a decrease by a stationary eddies. So this means that there is probably more cyclones and less anticyclones over the northern hemisphere, mainly during winter. And to look into more that what causes this, I plotted also the mean sea level pressure values from CSM. And what I found is that there's more semi-permanent low pressure systems due to paleogeography in the paleo setup. So we have the Icelandic low, which is in current climate, the Aleutian low, so to say. And there's also one in the Gulf of Alaska and also the Eurasian low or Siberian sea low. So that's probably the reason for the increased number of cyclones or transport by a stationary transient eddies. I don't know yet if there's more cyclones, but that's what I want to find out. So the conclusions is that the role of transport in polar amplification in the eco simulations is not clear, but the partitioning of meridional heat transport shows the changes in the different processes and the compensating mechanism also. And what we found that high CO2 values affect the circulation of the headley cell, it becomes more intense, and also the monsoon systems. And that in the paleo setup is changing the energy transported by mid-latitude cyclones and blockings, mainly in the winter period. So thank you for your attention. I hope you have some questions.
Great. Thanks so much, Fanny. You're perfect in terms of time.
I was shorter, yeah. Good.
And we do have time for one quick question. Unfortunately, I want to wait. Yeah, we're a little bit behind schedule. Yeah. Questions?
Can I ask a question about the method? So in the deep map model simulations, because of the high CO2 and the short length of the simulation, we may have some top of atmosphere radiation imbalance. I'm wondering how this is dealt in the heat transport calculation.
The imbalance is then, so I calculated in a way that at the poles, there should be no transport, so at the polar region. So then the imbalance is divided through all the latitudes.
Okay, thank you.
Yeah.
Great, thanks so much. I'm sure you have more questions. Please feel free to ask them in the chat. Our next speaker is Alex Thompson. Alex, please share your screen and begin. Great, I can see your screen. You want to switch the display mode.
All right. Hello, my name is Alex Thompson. I'm a postdoc at WashU in St. Louis, working with Braunway and Konecki, and today I'm going to share some results from a project I'm working on looking at moisture source and isotopic changes in the Yucatan Peninsula of Central America during the last glacial maximum. And I want to acknowledge Pedro, Jesse, and David there at the bottom for help with some of the original simulations here as well. Okay, so the broad motivation for this work is the fact that several generations of climate models have predicted drier Central American climate by the end of the century. As we can see on the left, precipitation reductions by as much as 40%, perhaps. And this is likely due to a southward shift in the Pacific to Atlantic ITCZ, which is pulling precipitation away from Central America and further south towards the tropical Pacific. So the problem, though, is that there are large intermodal uncertainties in this region, and this is precluding a robust assessment of these future projections. So in Central America, we can see on the right that there is considerable spread among these CMIP6 models in their rainfall projections by the end of the century, depending on the scenario and the individual models shown by the shading. We can see anywhere from slightly wetter conditions to much drier conditions. And so the IPCC also gives only a medium confidence level to this drying trend in Central America. So there's still quite a bit of uncertainty in these projections. So we want to better understand hydroclimate in Central America. And a great way to do that is to look towards the past. And specifically here at the last glacial maximum, which is a good time period for looking at Central America because it had a similarly southward shift in the Pacific to Atlantic ITCZ. But it's very important to note that rather than being forced by greenhouse gases, it was forced by Northern Hemisphere ice cover. So this means that the LGM is a good time period to try to separate some of these large-scale climate forcings and better understand some of the ways that hydroclimate in Central America responds to these changes. Now, looking at paleoclimate in Central America, it's a very under-researched region. So there are very few proxy records that exist telling us about climate in Central America. And even so, some of the proxy records that exist tend to contradict each other. So we don't have a great grasp on LGM hydroclimate in Central America. So we can't so far answer some very simple questions, such as was Central America wetter or drier during the LGM? And part of this is underscored by the fact that there's been little attention on LGM Central America in modeling studies. So we are trying to address this knowledge gap and specifically looking at Central American hydroclimate and how it responded to some of these large-scale forcings like ice sheets and greenhouse gases here during the last glacial maximum. And so for this study, we are aiming to quantify changes in rainfall and its isotopic composition from various geographic source regions. And the reason for this study design is that we are going to be comparing these model results with newly constructed proxy records from a collaborative research proposal that I will touch on at the end of this presentation. So to perform this research, we are using ICESM1 with water tagging capabilities. And I'm showing here this table of 4 different simulations that we have to pinpoint the roles of ice sheets and greenhouse gases in driving Central American hydroclimate. As you can see on the top 2 rows, we have 2 full types of simulations with the pre-industrial and LGM conditions. But then we also are running 2 single forcing simulations that hold a fixed pre-industrial climate, but then force it with either lowered greenhouse gases consistent with LGM levels or the presence of Northern Hemisphere ice sheets like we had in the LGM. So in these simulations, we have water tagging capabilities. And here I am showing the terrestrial and marine water tag regions that we have to look at rainfall and isotopic composition. And for those of you who maybe haven't looked at water tagging results or aren't as familiar with it, here's an example of what we could look at from tag 15 here in the North Atlantic. So essentially what this plot is showing is for the pre-industrial, any moisture that is evaporated from the North Atlantic surface is then tracked through the model, and then we can quantify where that moisture ends up raining out. So we can do something like take the Yucatan Peninsula region of Central America here and quantify the amount of rainfall that was actually derived from the North Atlantic. So that's exactly what we're doing in these simulations. And we're taking this Yucatan Peninsula, that tiny little red box, if you can see on the maps. And I just want to point out for the remainder of this presentation, I'm going to narrow down to the regions of greatest importance for the Yucatan, so we don't have so many distracting regions. We're just looking at 15 different water tags. So this is very much ongoing work, but I wanted to share some of my results so far. So first off, I'm going to start at seasonal hydroclimate. So looking in our pre-industrial simulation, we can see that rainfall in Central America is largely following the movement of the ITCZ and is high during the boreal summer. And looking at the vectors here are integrated vapor transport, we can see that the Caribbean low-level jet, which is this easterly flow throughout the Caribbean, is primarily delivering moisture from the Caribbean and Atlantic to the east. We can look at this a little bit differently now through the annual cycle average over the Yucatan Peninsula and see again that same high period in the summer for precipitation. But now looking at the full LGM simulation, we can see that rainfall year-round is lower than in the pre-industrial. Now comparing this to our single forcing simulations, we can better quantify how these large-scale forcings contribute to these rainfall changes. And when we look at the impact of greenhouse gas reductions on these climate simulations, we can see that they actually have a slight increase in rainfall, especially during that summer season. However, when we look at the impact of ice sheets, we see a decrease in rainfall year-round and very similar looking to that LGM simulation. So this is a great kind of categorical result. We can see that LGM drying is likely due to these changes in ice cover, but it's a fairly simplistic way to see this, and we don't really understand as much from looking at it this way how this change in rainfall actually manifests throughout the climate system. So a great way to do this analysis is to look at a water tagging analysis. And here specifically, I am looking at changes in rainfall. For the sake of time for this presentation, But I want to mention that I'm also looking at the changes in ice tablet composition. So if anyone is interested in these types of results, I'd be happy to discuss those after the presentation. So first of all, we can look at the pre-industrial simulation and see here that the vast majority, more than 80% of rainfall delivered to Central America is coming from the North American land surface, which is about 10%, the Caribbean, which is just over 30%, the Western Tropical Atlantic Ocean, which is about 30% as well, and then about 12% from the North Atlantic. So I'm going to focus on some changes from these different regions when looking at some of these results from our water tagging analysis. So first of all, looking at the tropical Atlantic and the Caribbean, we can see the change in the percentage of rainfall. So this is essentially telling us how important this region is to contributing rainfall to Central America. And this is the percent change due to the addition of Northern Hemisphere ice sheets. So I want to draw your attention to this big shift in the boreal spring, where we can see a much more important source is the tropical Atlantic, potentially at the expense of the Caribbean. And here on the left, I'm showing the integrated vapor transport and the evaporative flux. So I'm still digging into these results, and I think they're very interesting. Perhaps thinking about the southward ITZZ shift that ice sheets force here, we have some circulation changes downstream of this or that are related. So I'm still digging into this, but I think this is a very interesting finding so far. We can also see that the North American land surface becomes a much greater moisture source, a more important moisture source to Central America when we have LGM ice sheets. And even during the winter, we have a greater increase in this rainfall percentage. So perhaps ice sheets are changing types of circulation that lead to a greater importance from North America. And then lastly, we can see the North Atlantic becomes a greater source for moisture during the summer and potentially at the expense of the sum of other land and ocean regions, especially during this time. So, I think it's very interesting to see that perhaps there are some circulation changes in the North Atlantic subtropical high that are leading to more evaporated moisture and transport into Central America. At the same time, in the colder climate with Northern Hemisphere ice sheets, we perhaps see a shift towards more proximate regions of moisture sources, instead of these further afield regions. So just broadly to conclude on some of these results, we can see that the LGM was likely drier because of Northern Hemisphere ice cover. And specifically for this presentation today at the CESM Workshop, I think it's great to highlight the fact that water tagging is really allowing for further explanation of this change. I've only touched the surface of these changes that we can look at here, where we've seen that Northern Hemisphere ice sheets are shifting the ITZZ and possibly impacting circulation patterns that's changing the delivery of moisture to Central America. And so lastly, I just want to highlight the fact that this project is a part of this collaborative research grant, where specifically for this, we're looking at these LGM ICESM simulations, and we want to compare these to newly constructed leaf wax and GDGT records from Lake Petanitza in Guatemala. These records are currently being produced by organic geochemists from WashU in St. Louis, Notre Dame, and Pitt as a part of this collaborative research grant. So, this is hopefully going to lead to some great model data intercomparison in the future. And, potentially we're going to look at not just the LGM, but different glacial, interglacial cycles throughout these records. I think, this highlights a great collaboration between paleoclimate modeling community, as we have here today, and the paleoclimate data community, looking at these proxy records. And then, looking at these types of changes, we're also interested in looking at how this paleoclimate framework of water tagging and understanding these moisture sources may be able to allow us to look at how some of these changes in hydroclimate may impact future climate in Central America, and kind of use this paleoclimate framework in a future setting to better understand some of these hydroclimate changes. So thank you for listening to my talk today. Thanks to the organizers. I'll take any questions or depending on time.
Great. Thanks so much, Alex. You're on time. We have time for a quick question. I already saw one in the chat. Eleanor Martin, do you want to ask your question?
Yeah, sure.
Go ahead.
So I was really interested in your seasonal cycle of rainfall and how the first rainfall peak seemed to change dramatically between your different simulation types. So sometimes there was a hint of it and sometimes there wasn't, and what you think was some of the reasons why that was happening.
So I think you're talking about this peak right here.
Yes, that's right.
Yeah, I think that's really interesting, and I haven't looked into why this is happening yet, but that's definitely on my to-do list. And I think it's interesting to see that in the case with greenhouse gas changes, we still have it, but with the ice sheets, we don't. So perhaps some types of early season circulation changes that the ice sheets are initiating is kind of the first place that I would look. But I think that's a great question that we don't know the answer to yet, and I want to find that answer soon. Thanks for the question.
Wonderful. For the sake of time, we're going to move to our next talk. Our speaker is Yuntao Bao. Yuntao, please share your screen and begin. Is Yuntao here?
Maybe his audio is not connected.
Hi, John.
Okay.
Yeah, I'm sorry. So my apartment is powered cut, so I think my connection is not stable. Can I present later? I will find a place later. I'm so sorry for that. It's emergency.
Let's switch to our next talk, and then perhaps we can give it another try after our next talk. All right, so let's switch to our next talk, which is given by Jesse Valavito. Jesse, are you there? Feel free to share screen and start.
Okay, let me see if I can get the share screen working. I was playing around with operating systems just a second ago. So let me know if this works. Can you see the title?
Yes, perfect.
Okay,
and we can hear you as well.
Great. Okay, so let me get started. So I'm presenting a Eustatic sea level rise compatible model for the younger Dryas. This work has been done with Deepak Chandan and Dick Pelche at the University of Toronto. I presented some earlier work of this at the last Paleoclimate Working Group meeting. So I'm going to move somewhat quickly through the introduction so that I can get to the kind of new results. So introduction, we all, I think, know what the younger Dryas is. In our model, we're kind of pegging it at 12.8 thousand years ago to 11.5, which is pretty standard. It's known to be caused by a release of fresh water from proglacial lakes on the edge of the Laurentide into the Arctic Ocean through the Mackenzie River outlet. And the outflow of fresh water seems to have subdued or shut down, depending on the terminology you want to use, the AMOC for about a millennium. The picture on the right there is the Dryas octopetala flower, for which the younger Dryas is named. So there have been lots of prior modeling attempts to try to get a climate response from a GCM by injecting fresh water into the ocean. A recent paper by Love et al. Summarized a number of these prior modeling attempts and identified a few key areas of improvement or areas where the models weren't quite accurate. These were forcing strength, forcing location, and boundary conditions. Many models apply extremely strong forcing to the North Atlantic with LGM boundary conditions. We're talking something like, 5 SV for 100 years, Stradrops, I mean. So not only is this forcing too strong, but because it's being applied for a long time, the total water volume is incompatible with sea level records. So an example of this is if you look at a recent modeling by Hay et al. In 2021, they apply quite a large amount of forcing over the entirety of the Younger Dryas, which leads to an unrealistically large increase in sea level. With the boundary conditions, part of the issue is that if you use LGM boundary conditions, they're quite different from those that existed at the Younger Dryas time. There's some debate as to whether or not the Bering Strait was open or closed at this time, and of course, just ice sheets are going to be in different configurations. This is because sea levels are significantly higher at Younger Dryas time, and ice coverage is much more limited. So in terms of some of the proxies that we're trying to use here, Kaigwan et al. Found 2 IRD layers in the Beaufort Sea, one at 14,500 years ago and one at Younger Dryas time. This weaker later at Younger Dryas time, you can see it's on the left side of that graph. And so they also found evidence of maybe light forcing for about 800 years preceding the Younger Dryas, kind of thinking of a slow leak of freshwater before the outburst flood. So in Tarasov and Pelche, they argued that the peak flow rate couldn't be much more than about 0.2 Sverdrups, but there's some debate about that. And in terms of what we're using to constrain, with the proxies that we're using to constrain, there's the Barbados record, which constrains RSL rise to be somewhere in the vicinity of 5 meters during this time. That's not a very tight constraint. Later on, I'll talk a bit about some of the constraints imposed by lake volume analysis. And just as a caveat that this increase includes all RSL contributions across the world. So if there's melting going on in Antarctica or Greenland or Fennoscandia, then that's going to be picked up by the Barbados sea level record and can't be attributed directly to the Younger Dryas. So some quick numerical facts. We use CSM1, constant background and dipycnal diffusivity. Tidal mixing and overtides are turned off. For orbital parameters, trace gases and orography, the thermometry, that's all set to 13K. The one caveat from perfect boundary conditions for Younger Dryas is that the land sea mask is left at LGM. This had to do with the difficulty in getting the system to actually spin up without it. And so the way we dealt with this was just by treating the Barents Sea as land of extremely low height because it's deglaciated by Younger Dryas time, but not at LGM. We decided to keep the Bering Strait closed. And we integrated for 2,300 years till the AMOC stabilized and then started doing our forcing runs. So in terms of forcing runs, we have 2 main types, low and slow, where we force at a very low amount for the entirety of the Younger Dryas for about 1,000 years, and then hard and fast. So this was very interesting. When we force it fast enough, we can actually just do a short period of forcing, and then the AMOC will stay dead for about 1,000 years. And by dead, I mean just depressed by a significant amount before recovering. And so this 1,000-year time scale jumped out at us as very nearly exactly what the Younger Dryas was. So we started to spend more time looking at these types of simulations. So here we have all the different simulated collapse scenarios. As you can see, we've run quite a number of them. I'll get into some more details about specific ones. But what you see here is runs that differ by forcing amount and duration of forcing. One of the key facts here is that once a run collapses, it recovers exactly the same. The only difference is when it passes a certain threshold. As you can see with the yellow line here, which was our weakest forcing run, I'll talk about it in a second, because it took longer to collapse, the 1,000-year time scale pushes it a little bit forward. But with the red and the blue runs, you see, because they collapse at the same time, they take exactly the 1,000 years after that collapse point, they both recover identically. So here are 3 extreme runs. There's our quickest collapse, which was hosing for 1 year at quite a high value of 6 SV. Our lowest forcing collapse, which is the lowest total volume, where we forced for 5 years at 1 SV, and our borderline collapse, which was the weakest forcing that we could find a collapse for, which was 1.25 SV for 115 years. These are all summarized here. These are all of our various forcing runs that collapsed. There's some more that collapsed, but they're very similar. And so we're comparing this against an estimate of glacial lake volume from around the 8.2 kiloyear event. It's somewhat difficult to find good estimates of exactly how much the lake levels would have dropped in Lake Agassiz, Lakes McConnell, and other glacial lakes. So we use the 8.2 kiloyear volume estimates as a pseudo proxy for what we could expect. And so what you can see is that 3 of our runs here are significantly below the glacial lake volume, which is of course not a very tightly constrained proxy. And our 0.2 run is only a little bit above. So it looks like we have a few different types of runs here at various forcing levels and durations that could produce the collapse we're looking for. So over here, we see a bunch of runs that didn't quite collapse. So as we were testing runs, we'd get to a point for a given forcing where our forcing duration was too short to create a collapse, and we get an immediate recovery. So once we noticed that this was happening, our next step was to try and fill out a phase diagram of duration versus forcing strength to see what that might look like. So we have a figure here where the red dots are collapse and blue are no collapse. And you can see that there's this kind of this relationship where as you go to shorter duration, you need more volume. And this is a log scale, so we can show it on a nice graph here without being blown out. But what might be more instructive is to look at the total volume versus duration, where we see an almost linear relationship. As we force for shorter amounts of time, we need less total volume, which is interesting because there is some evidence that the Younger Dryas was a very quick forcing event. And so the quicker we make it, the less volume we need. So in terms of what the recovery looks like, when it recovers through the opening of a polynya in the Erminger Sea. This happens in February it depends on the model year of the model we're running. This is very similar mechanism to what's discussed in Peltier 2020 with respect to Dansgaard-Oscar oscillations. And it's very sensitive to the forcing strength, right? If we're just a little bit too slow, we don't get this type of opening. So in terms of comparison, we wanted to compare this to the 8.2 kiloyear event. This is where we, instead of forcing in the Arctic, we forced in the North Atlantic. We did 3 different runs here, one with a 6 SV run for a year, a 0.6 SV run for 10 years, and then a 0.2 for, I believe it was 100 years there. And as you can see, in all of these cases, the minute the forcing is turned off, we get an immediate recovery. So what this shows us is that the boundary conditions, because for the 8.2 kiloyear event, we used appropriate boundary conditions, that whether or not the AMOC stays turned off is extremely sensitive to those boundary conditions. So that's very interesting. Not shown here, but we actually did try forcing in the North Atlantic with the boundary conditions of YD, and we did find that stayed collapsed. So this is not location based. This is boundary condition based, a difference in effect. So in terms of conclusion, where we're at now is that we've been able to produce a model of the YD using very reasonable amounts of freshwater forcing in the proper location with proper boundary conditions. This includes accurate trace gases, orb parameters, and the orography. The one caveat is this land sea mask, but we're showing clear evidence of on and off states in the AMOC. And what's I think most important here and most interesting is that we get this 1,000-year natural duration of shutdown without having to put that in by hand. We just get the time scale of the Younger Dryas out of the model without any attempt to make it so. So as for future work, where we're going with this is we're working on writing up the results right now because we've done a very large number of sensitivity tests to see what that curve looks like. But yeah, so that's what where we're at right now. And I guess as a kind of conclusion, if anyone in the audience knows of some good estimates of volume of water involved in the younger Dryas. That would be interesting for us to see, or if anyone has any specific information on, based on kind of geologic features, what the peak flow rate could have been in that region to help us constrain it further. That would be interesting stuff to hear from you guys. So with that, here's my citations, and I'm open for questions.
Wonderful, you're on time. We have time for a quick question. Yeah, I already see a hand up. Aishu, please ask your question.
Yeah, this result is very interesting. And I just wonder, when you put in freshwater into the Arctic, for those simulations with a southern year AMARC shut down, is the sea ice in the North Atlantic is pretty extensive or not?
Yeah, so I'll go back to the Polynya feature. So this is what the sea ice looks like. You can see it's up to 100% right down to like Newfoundland in the west, and almost past what is that, the Bay of Biscay on the right. So yeah, we have quite extensive sea ice once we've applied the fresh water.
Okay, maybe that's why it's sufficiently prevent the deep current to occur in the subpolar North Atlantic.
Sorry, I didn't quite catch that. What was
I mean, with this more extensive set coverage in the subpolar North Atlantic, it will prevent the deep convection to occur in this region.
Yes, yeah, I think that's what's happening, because when we don't force it enough, we force it for too little a time, it doesn't create the same extent of sea ice that shuts down the North Atlantic deep water production.
Thank you, very interesting.
Awesome. Yingtao, are you there? Okay, since Yingtao is not here yet, hopefully he will join us later. I will switch the last talk of the Paleoclimate Working Group, which is my talk, to now. Later on, if Yingtao can join us, then he can give his talk. Right. Good morning, everybody. Today, I would like to share with you some of the new results that we get from studying the lake pricing. Specifically, I would like to talk about the boundary condition dependency of temperature responses to CO2 forcing. Before I jump to this topic, I would like to give you an overview of the suite of Pleistocene modeling comparison project 2 experiments that we have. So we completed and published the Pleistocene modeling comparison project 2, Climate 2 baseline experiments. We used the 1 degree nominal resolution for all model components, and the simulation were run for 3 generations of CESM, from CESM 4 to CESM 1.2 and CESM 2. Those simulations are run with targeting mid-period transient with 400 ppm CO2 and mid-Pleistocene boundary conditions. From then, we actually now have a suite of single forcing experiments when we force the model with either Pleistocene vegetation ice sheet changes or Pleistocene topography bathymetry, or just the CO2 only. And we have published some of the results using those simulations to understand the hydroclimate across Asia and Africa. And if you're interested in exploring aspect of Lake Pleistocene with any of those simulations, a lot of data are already available. I can point you where to download them, and if data are not available, I'm also happy to share them with you. So by looking at the simulations, I noticed something really interesting, which is this boundary condition dependency of temperature responses. What do I mean by this? If you compare showing the top panel here, if you compare the surface temperature change between 400 ppm CO2 and the pre-industrial level of CO2 with pre-industrial boundary conditions to the simulated warming for the same amount of CO2 increase with Pleistocene boundary conditions, the warming with Pleistocene boundary conditions is actually 18% greater And this translates to about 0.8 Kelvin difference in equilibrium climate sensitivity, whether you estimate it with this warming or this warming. If we remove the global mean warming out of those two maps, you can see that the warming pattern is actually not that different. However, it looks like across the ocean, with Pliocene boundary conditions, the CO2 increase actually induced a slightly enhanced warming pattern. I would argue that this dependency of warming on boundary conditions to the same amount of CO2 increase can be explained by the dependency of warming on CO2 to background warmth. And this is shown by pseudo mixed layer ocean experiments. I conducted two sets of those experiments with CESM2 at 1 degree resolution. One set I prescribed pre-industrial boundary conditions and ocean heat flux. And CO2's increased from pre-industrial level to 590.6 ppm with 1 watts per meter square incremental increase of forcing from 0 to 4 watts per meter square. The other set, I prescribed Pliocene boundary conditions and ocean heat fluxes, and with 3 different levels of CO2. And those Pliocene boundary conditions, the prescribed CO2 level in the Pliocene mixed layer ocean simulations are also scaled to reflect the increase of CO2 forcing equivalent to 1 watts per meter square from pre-industrial to 3 watts per meter square. So you can see that the simulated amount of global warming per 1 watts per meter square of forcing shows a linear relationship or increases with background global mean temperature. The simulated results are showing those red dots. What you would expect if there's no background dependency is this gray dot. So you would not have different amount of warming corresponding to 1 watts per meter square forcing, regardless of background global mean temperature. And the blue dots are the simulation with Pliocene boundary condition and heat fluxes. And you can see it roughly follows this linear relationship. So this demonstrates that this dependency of warming on Pliocene boundary conditions is perhaps more fundamentally reflects the dependency of warming on background warmth with CO2 forcing. So what causes this dependency of temperature response on background warmth? If we go back to the most basic energy balance model and the definition of equilibrium climate sensitivity, we can find the answer. So the simple energy balance model at the top of the atmosphere is showing here. So the TOA, top of the atmosphere, radiation imbalance N equals the forcing minus the radiative response, delta R TOA. We can carry out Taylor expansion of radiative response as a function of surface warming. Delta R equals the first derivative of delta R as a function of surface temperature change times the temperature change plus second derivative divided by 2 times the surface temperature change to the second, so on and so forth. Typically, we keep the first order term of the Taylor series, which is delta R TOA is approximated by the first derivative times the amount of temperature change. If we plug in this expression in our simple energy balance model, we get the TOA radiative imbalance equals forcing minus first derivative of delta R times the surface temperature change. And this is the equation used by the Gregory method to infer the equilibrium climate sensitivity delta TS for a doubling of CO2 experiment. Right, at equilibrium after doubling of CO2, forcing is balanced by the delta R first derivative times the temperature change, and temperature change is the equilibrium climate sensitivity. Sorry. So the question is the first order approximation good enough for CESM2? I would argue it is not. This is showing in this chart here. So this is on the y-axis, this is showing our linear forcing designed for a mixed layer ocean simulation from 1 watts per meter squared to 3 and 4 watts per meter squared. And you can see this red dots corresponding to the simulated amount of warming corresponding to those linear forcing. And you can see the distance between the red dots along the x-axis actually increases with the amount of forcing. And this nonlinearity result in a greater warming if we're following the true or better nonlinear model compared to if we follow a linear fit. And at 5 watts per meter square, the linear model would suggest 7.35 Kelvin warming. However, following the nonlinear model, the second order polynomial model, you actually would get 9.15 Kelvin warming. And notice that the coefficient for the second order polynomial term is actually negative. All right, so based on the CESM2 results, it looks like we do need to keep the second order term of the Taylor series. So in this case, forcing is balanced by radiative response at equilibrium. However, in this case, radiative response is approximated by the first derivative times delta Ts, but also added with the second derivative divided by 2 and times delta Ts to the second. This is based on our second order polynomial fit. Following the definition of net response parameter, so we're going to take the response and divide it by the amount of surface warming. In this case, you can see that this response parameter is a function of the amount of surface warming has incurred. And for CESM2, like I mentioned, this the coefficient for the second order polynomial, this term is actually negative, which suggests that the response parameter actually decreases with warming. So given that the forcing is balanced by response parameter at equilibrium times the amount of warming, increasing background warmth as a result would increase climate sensitivity. I don't have a lot of results, but I want to show a quick first order diagnostics to see where is this rise of response parameter nonlinearity from. For every watts per meter squared linear increase of forcing, I calculated the amount of changes in the top of the atmosphere reflected shortwave radiation, and I calculated the changes in the planetary emissivity. The results are plotted here. Again, x-axis is the linear increase of forcing, 1 watts, 2 watts, 3 watts, and to 4 watts per meter squared from the pre-industrial. On the y-axis shows the changes in the reflected shortwave radiation. As you can see, the relationship between the changes in the shortwave reflected shortwave radiation and the forcing is nonlinear. So there is a reduction, there is a decrease. So the reflected shortwave radiation actually decreases more at higher forcing compared to at a lower forcing. This suggests enhanced positive TOA shortwave feedback. Similarly, I looked at the long wave response. Again, there is a greater amount of long wave trapping at a higher forcing compared to at a lower forcing. This again suggests enhanced positive long wave feedback as well. So here are some quick thoughts about the implications to paleoclimate. So those results seem to suggest that estimating equilibrium climate sensitivity from past warm climate really have to consider the background warmth if those CESM2 results are proven to be true. And it's perhaps less useful than estimating the net response parameter in terms of understanding what's happening in the system. hopefully I've showed you that ECS varies substantially with background warms, and this is tied back to nonlinearity in both shortwave and longwave TOA responses, and of overarching or a little bit of speculation is this perhaps offers an explanation for warm climates with moderately elevated CO2, such as Miocene, regardless what CO2 reconstruction you're looking at. It's generally less than 2 times CO2, yet the global mean temperature is 5 to 6 degrees warmer. Hey, thanks so much. I will take one quick question if there are any, and we can have a short break afterwards.
I can ask a question if nobody else.
Go ahead, John.
Okay. So maybe I missed that. How did you come up with the precise forcing in the model?
Oh, that's a good question. So I used the CO2 level. I used the calculation 3.8 watts per meter square for doubling of CO2, and use that to scale the CO2 levels that correspond to 1 watts per meter square forcing.
Okay, I see.
Increment from 0 to 4. Yeah.
Yeah, if so, I think I can add a quick comment.
Yeah.
So that a simple equation may not work for the model. So in the end, in the model, what you get about the forcing may not be precisely like 1 to 4 watts per meter square. There's also fast adjustments in the system.
Okay. Yeah, I will look at the prescribed SST runs to take another look at the forcing. All right, awesome. Thanks everybody for participating in the first session. If people want to hang out and chat more over Zoom, I think we can leave the window open, right, John?
I think it's time for the break, and Todd can help us show a slide during the break.
Okay.
And people, please come back at 10:40. And our co-chair, Samantha, will chair the second session. Thank you, everyone.
Thanks so much.
Hey, Ran. Hi, I put Young Tao's presentation in the afternoon. Is that the correct time?
Yeah, yes, that's perfect.
Okay, sounds good. We're in the next session.
Thank you, Todd.
Thank you.
You're welcome.
Aaron, I have a logistical question also. What were you setting the timer for people? Was it 12 minutes or 15?
I set it as 12 minutes to give them a note, but I usually press the button a little late.
Sure.
And, so I think it's probably roughly like 2 minutes they can have after I set the timer to 12 minutes.
Okay, sounds good. So yeah, so we can start with the Tao's talk and then move to the regular agenda, I guess. Cool.
Yeah.
All right. Awesome. I guess we should give people a minute to kind of trickle back in. It's always hard to tell who's actually here on Zoom.
I
guess Pedro.
34.
Sorry?
We have 34 now.
Yeah, hopefully everybody's actually at their computers. I guess the most important thing, Pedro, are you here?
I'm here.
Okay, cool.
Thanks,
I guess we'll put you. Hey, so get you first on the agenda. We'll put Yuntao at the end. Yuntao, is that okay with you? Do you have to go?
Yeah, it's good for me.
It's good. Okay, cool.
Yeah.
All right. Well, yeah, I guess we can stay on time then. So we can get started with our second session of this morning. So yeah, our first speaker in the second session is going to be Pedro De Nisio, speaking about an ensemble of hosing simulations to help predict future changes in tropical climate. So Pedro, take it away. You can share your screen and all that, right?
Hello, everyone. You can see all my calculations. Hold on. I want to show my video. Okay. Okay. Ready to go. I changed the title a little bit because I realized the abstract was too long and confusing, but it's the same idea. I want to thank all my co-authors and NSF for all the great work on this paper, which we're about to submit. So I thought it would be time to just share with you the final results. We all know that the abrupt events that punctuated the last glacial period produced large changes in the tropics. So here we have records that I'm sure everyone is familiar with: Greenland temperature, the Cariaco Basin record that tracks the rainfall or hydroclimate associated with the Atlantic ITCC, and in red in the middle, and a record from the Indian monsoon. And by the time this record from the Indian monsoon was produced, we all realized that abrupt events had a global influence in the tropics. And you can see here Henrik Stadial 1 with cooling over Greenland and pronounced drying over northern South America, where the Cariaco Basin is located, and also drying of the Indian monsoon. So our understanding of these mechanisms, the mechanisms that drive this global response, is far from complete. There's a long story of hosting simulations, which are used to weaken the AMOC. We had a lot of presentations today about that, but there's a lack of a coordinated protocol or a multi-model approach. And model data evaluations have been limited until now. There's a few regional evaluations or using just one single model, and some other ones have inconsistencies on how the hydroclimate response to a change in the AMOC or during the abrupt event is isolated relative to the rapid deglacial changes that happened alongside with these events. And the other one thing I want to remind everyone that this might be important for understanding future changes, because we expect potential weakening of the AMOC in the future. So we took the approach of producing a global synthesis of all the information that we have from Henrik Stadial 1 in terms of hydroclimate in the tropics. And you can see in this map all the sites with rainfall sensitive records and how we classify them into whether Henrik Stadial 1 was drier, wetter, or unchanged relative to the deglacial baseline onto which the event happened. So we think that defining the hydroclimatic signal relative to the deglacial baseline is the correct way of isolating the specific response to a change in the AMOC, or at least to cooling in the North Atlantic. So you can see highly coherent patterns across the global tropics. And I'm going to get into more detail on what we think they mean later on. But there's an abundance of records from the tropics now. We should be amazed by all this amazing data. Each one of these records is just someone going to the field producing a record. We focus on hydric stadia 1 because it has a relatively large signal relative to other abrupt events like stadia 2. We know the glacial back constraint better. It was close to full LGM conditions. And since it's one of the most recent ones, there's more records that we can use to reconstruct these patterns. And we compare these reconstruction of the patterns with an ensemble of freshwater hosting simulations. This is not a coordinated ensemble, so it's an ensemble of opportunity. It's just all the simulations we could get our hands on. They're based on the Kageyama 2013 study. So we kept 9 simulations from that ensemble, and we added another 8 with newer models. That all run relative to glacial conditions. Most of them are LGM background conditions, and then freshwater forcing is applied. Different rates, different locations, and again, the ensemble is not done in a coordinated way, but most of the freshwater forcing rates are realistic or consistent with the record of sea level rise during these events. But the one thing I want you to focus on is that the diversity of rainfall responses. So the maps to the right are the 17 simulations showing the changes in annual mean rainfall. And you can see a range of responses in intensity, but also in patterns. And I'm going to get into that in a bit. So the first thing you will see is that the simulated and the proxy inferred changes resemble a shift in the intertropical conversion zone, which is one of the leading theories of how the tropics responds to changes in the AMOC or cooling of the northern hemisphere. The bars are the number of sites that are drier in different latitude bands, which you could have inferred this from the map I showed you before, but if you want to be quantitative, we have a predominance of sites in the northern hemisphere showing drier conditions and a predominance of sites in the southern hemisphere showing wetter conditions during hydric stadia 1. And then the solid line is the ensemble mean, annual mean, zonal mean rainfall change simulated by the models, and the spread is the min max range. So you see that all models simulated zonal mean shift in the ATCC. There's this little kink that is very interesting. Some models do not show weather conditions in the northern hemisphere here, but on average, we see this zonal mean response. But when we compute the agreement, and if you've been following our research, we use this Cohen's kappa statistic to estimate agreement between patterns simulated by models and proxies in categorical form. When it's 0, it means no agreement. When it's 1, it means perfect agreement. Here you have all the simulations, all 17, and they show a wide range of agreement with the proxies from close to 0 to pretty high up here. 0.6, it's super high. The Cohen's kappa statistic normalizes for random agreement, so it's really difficult to get to perfect agreement. Every single side will have to agree with a simulation too. So what is driving this diversity of agreement? Well, we can look at the reductions in the AMOC strength across all these simulations, and we don't see a clear relationship. We could argue that maybe a stronger AMOC reduction will drive a stronger tropical response and better agreement. We could look at cooling in the North Atlantic, where the AMOC has the largest influence, and I would argue we don't see a clear connection. Models simulate a lot of cooling, others simulate very little cooling. And the last quantity we find a bit of more of a consistent relationship was the magnitude of the cooling over the tropical Atlantic. Although it's not clear cut, you have exceptions, but models that simulate moderate cooling. So these models that are here towards the right, I'm showing them with my pointer. Oh, and I circle them. those show cooling over the tropical Atlantic. So this is the Caribbean and the Western tropical Atlantic of roughly 2 or 3 degrees. And those are the ones that show the highest agreement, although we have 2 models here that don't show such high agreement. But there's a tendency that the stronger the cooling in this region, the higher the agreement. So we're going to take an ensemble mean approach to look where this agreement is coming from. But before we do that, I just want to show you what the patterns of cooling look in the Atlantic. So we group the models into 3 different groups based on the magnitude of the cooling over this domain in the Caribbean and the Western tropical Atlantic. The domain in red, moderate, strong, and muted. And you can see that averaging the responses of all the models, you can see distinct patterns there. So first of all, I want to show you the models that show the best agreement, the ones with moderate tropical cooling. And I think this is mind-blowing that you have all these sites with records that are rainfall, that are use proxies that are sensitive to rainfall, and the patterns agree with such detail. I mean, there's so many places you could look at. But on this group of models explain or agree with the proxies almost all over the tropics. So let's look into the details. So on the left, I'm showing the 3 different groups of models showing the annual mean, ensemble mean rainfall changes. So on top, the moderate cooling ones, the middle, the strong tropical cooling. There's 3 models that show a lot of cooling in the tropical Atlantic. And then on the bottom, the ones with muted tropical Atlantic cooling. So you see that all of them have a shift of the ITCC in the Atlantic with different intensities, but it's quite coherent and not that different. But the model, when we compute the kappa value, so the model proxy agreement for the ensemble mean patterns now, so we're not looking at individual simulations, just the pattern simulated by all these the simulations in each group averaged together, we see what we saw in the previous figure, that the models with tropical cooling show higher agreement over the entire domain, this domain in the global tropics. So where is this higher agreement coming from? Well, it's not coming from the Atlantic, and you can clearly see with the naked eye that all 3 types of simulations capture the patterns in the Atlantic domain. So the Atlantic domain is sites in land masses surrounding the tropical Atlantic. And the difference is actually coming from the rest of the tropics. So we can see a much higher agreement for the models with moderate cooling, and a bit less for the ones with strong cooling. We think that those models overdo the response, and at some point they start not agreeing in some of the boundaries of the responses. And the ones with muted cooling show much weaker agreement, which less statistical significance. So I'm shading these bars based on the statistical significance of the kappa values. So let's look at the differences in the rest of the tropics. So we divided the domains, our global domain, into different regions and computed the kappa values regionally. So we have in Caribbean and Eastern Pacific ITCC domain. So it's all these sites along the eastern coast of the Americas. And on that domain, our models with moderate cooling are the ones that best explain the paleo data, although the strong cooling also simulates patterns that explain the data. And here we have the highest value. 0.7 is a lot, almost perfect agreement. Muted coolings that's not explains the patterns, although it shows some agreement, because you can see here that those models still produce some drying over Central America. If we focus on the water circulation, so in a domain across the Pacific, and here I'm going to show you the domain here with my pointer. It's a domain across the Pacific, east to west. There's theories on how.
1 minute warning.
2 minutes. Okay, perfect. So we also see that the moderate cooling gives us a much higher agreement, although not with the same levels of statistical significance because the proxies are a lot more noisier there. And then if we focus on the sites around the Indian Ocean, which capture changes in the East African, Indian, and Australian monsoons, we see also a similar feature with the models with moderate cooling, best explaining the paleo data. So I'm going to jump into conclusions. So the first thing is that a reduction in AMOC strength explains the changes in tropical climate during HDL1. We found that tropical Atlantic cooling is the key link between the changes in the AMOC and the tropics, and it amplifies the rainfall response. And the magnitude of the AMOC changes or the highlighted cooling is not as important. And if you recall the review paper in 2008 by Clement and Peterson, they proposed two mechanisms. The zonal linkage to the tropics with mostly zonally asymmetric responses triggered by the tropical Atlantic. And that's essentially what we find, that this mechanism is the one that explains the data. And this more zonally symmetric adjustment does not explain the data. And this is what we see in the models with muted cooling in the tropical Atlantic, more of a zonally symmetric shift in the ITCC. So I'm going to just show you that you can see the same behavior for the future. And I'm just going to show you this figure where we stratified future predictions into these different patterns of relative cooling over the tropical Atlantic. And we see massive discrepancies in their predictions for rainfall. You can focus here on the Caribbean and the Amazon, but there's a lot of other regions where the discrepancies are huge, and it could be a main source of uncertainty in future predictions, how the tropical Atlantic responds to changes in the AMOC in the future. So I'll stop there. Hopefully there's time for a question.
Okay, great, thanks. I think unless there's a very quick question, anyone? We're slightly over time. Okay, great. Well, yeah, thanks, Pedro. That's really interesting. Yeah, if people do have questions, feel free to put them in the chat. We can have a discussion that way as well.
Trying to.
But in the meantime, I guess we'll move on to Keifan Chen, who is our next speaker, who is going to be speaking about drought and volcanic eruptions influencing the history of China in the context of the Ming Dynasty megadrought.
Okay, I will share my screen. Hello, everyone. My name is Keifan Chen from Meridional University, and I'm a visiting student of the Ohio State University. My advisors are Professor Zhenyu Liu and Professor Liang Ning. Today, my topic is one drought and one volcanic eruption influenced the history of China, the Ming Dynasty megadrought. This is the outline. First is the motivation. The Ming Dynasty megadrought occurred at the end of the Ming Dynasty in 1637 to 1643 against the background of the Little Ice Age. This unprecedented 7-year megadrought is one of the most severe drought events in China in the last millennium, which gave rise to severe social and economic problems in the late Ming, such as famines, disease, peasant uprising, and so on, which strongly contributed to the collapse of the Ming Dynasty and at 1644 and significantly influenced the Chinese history. Well, I can't go down, okay. Many efforts have been devoted to studying the mechanisms behind severe drought over Eastern China, like the Ming Dynasty megadrought. Previous findings confirmed that decadal megadroughts in Eastern China are primarily caused by internal variabilities such as PDO and AMO changes. On account of this, external forces such as volcanic eruptions can also influence precipitation changes in Eastern China in multiple timescales. For example, on decadal timescale, volcanic eruptions can influence Asia summer monsoon by Atlantic multi-decadal oscillation tide connections and negative PDO phases. On decadal timescale, volcanic eruptions can influence ENSO events and result in rainfall decreases in monsoon regions. Previous studies also pointed out that the Ming Dynasty drought may be related to volcanic activities. However, the mechanisms triggering and maintaining the Ming Dynasty drought is unclear. Why does this drought persist so long and be so severe? So in this study, we investigated the mechanisms behind the Ming Dynasty drought from the combined effects of internal variability and volcanic forcing. In this work, we used the reconstructed Dryas index and precipitation in East China. We also used 13 CESM LME or forcing simulations. We reproduced the Ming Dynasty drought by volcanic sensitivity experiments using CESM. And in this paper, we defined drought as negative precipitation anomalies lasting for 5 consecutive years with maximum precipitation anomalies lower than 1 standard deviation. And this is our research region. Firstly, we studied the severity and evolution of the Ming Dynasty drought. In this figure, the blue lines are reconstructed precipitation changes during the past 500 years. The red line is the magnitude of volcanic eruptions. We can see that the precipitation decreased significantly during 1637 to 1645, which persists more than 7 years. The magnitude of this drought is close to 3 sigma and is one of the largest drought events in China in the past 500 years. According to the two reconstructions, there are no strong external forcings at the beginning of the drought at 1637, which means this drought may be triggered by internal variability first. The rainfall minimum occurred at the middle of the drought around 1641, which coincides with the eruption of Mountain Parker in the same year. The dry conditions persisted about 4 years after the eruption. As a consequence of this, we hypothesized that this drought may be initially triggered by internal variability in 1637 and was then amplified and extended by the eruption of Mountain Parker in 1641, generating a 7-year drought event. To verify our hypothesis, we studied the impacts of internal variability, volcanic forcing, and their combinations respectively. Firstly, we studied the probability of the occurrence of the Ming Dynasty drought if it is triggered by internal variability only. Here we used the Monte Carlo method. Firstly, we generated 2000 Reynolds Monte Carlo time series for 1000 years. This is one of the time series. We counted the frequency of drought with 7-year lengths and about 3 sigma intensity, which is the same with the Ming Dynasty drought in each of the 2000 time series. And then we draw the probability distributions of drought frequencies on the right-hand side. In this figure, the x-coordinate is drought frequency and y-coordinate is the probability of the drought frequency. We can see that if the Ming Dynasty drought is a natural event, the probability of its occurrence is only 10%, which is very small. Therefore, the Ming Dynasty drought has a small occurring probability if it is merely caused by internal climate changes. The superposition of external forcing can improve its occurring probability. Then, our superposition mechanisms can be examined by comparing drought events with and without volcanic influences. In this figure, The blue lines show the ensemble mean drought events from the 13 all-forcing CESM LME simulations in the past millennium. In the first figure, the droughts are influenced merely by volcanic eruptions without a natural drought occurred before the eruption. And we can see that the drought persisted nearly 2 years after volcanism. In the second plot, the droughts are triggered by internal variability only without volcanic forcing. The drought ended with a wet event after about 4 years. However, in the third plot, if natural drought occurred before volcanic eruptions, the drought will persist longer afterwards. This indicated that the combination of internal variability and volcanic forcing can amplify the drought and extend it for about 3 years. We further investigated our hypothesis by doing volcanic sensitivity experiments. Firstly, we selected 15 drought events induced by internal variability from a 500-year control simulation. Each drought persisted 3 to 5 years, which equals the first half period of the Ming Dynasty map drought. Then we added volcanic forcing of Mountain Parker into the last year of each of the 15 drought cases. This is the ensemble mean precipitation anomalies in the control simulation and volcanic sensitivity simulation. It can be seen that without volcanic forcing, the drought lasts for about 5 years, ending with a wet event. However, volcanic eruptions suppressed this otherwise wet event and prolonged the drought up to 3 years. This is consistent with observations and highlights the roles of internal variability and volcanic forcing in triggering and extending droughts respectively. Then we further investigated whether volcanic impacts remains the same when the eruption occurred in different drought phases. Here, we carried out another 2 groups of volcanic sensitivity experiments with volcanic aerosols added in the late and early stages of the 15 drought cases. In this figure, the red and blue lines are ensemble mean precipitation anomalies with volcanic forcing added to the last year and the second year of a natural drought. Figures on the top are control simulations. Figures in the middle are volcanic sensitivity experiments, and the figures at the bottom are differences between sensitivity and control simulations. We can see that the late phase volcanic eruption can have greater impacts on drought persistence and intensity, while early phase volcanic eruptions induce modest and weaker impacts. So the response of drought are nonlinear to volcanic eruptions occurring at different drought stages. And this is also consistent in reconstructions and CESM LME simulations. So the eruption of Mountain Parker is more likely to occur in the late phase of a natural drought. Then we investigated the mechanisms behind the Ming Dynasty map drought. Firstly, the volcano-induced cooling contributed to decreased land sea thermal contrast. This finally results in high pressure over land and low pressure in the ocean. This resulted in the weakening of the East Asia summer monsoon. On account of this, the variations of soil moisture over eastern China and the eastward retreating of the West Pacific subtropic high also contributed to the extended drought after volcanism. However, the weakening of land sea thermal contrast and the retreating of West Pacific subtropic high are consistent in late phase and early phase sensitivity experiments, which cannot explain the nonlinear response of drought but the soil moisture are different in these two experiments. In this figure, the red and blue lines are soil moisture changes in late and early phase experiments. The bars are precipitation. The soil moisture response remains strongly negative for about 5 years after late phase volcanic eruptions, while there is a small negative moisture response to early phase eruptions. We quantitatively calculated the soil moisture feedback on precipitation following previous methods, and we find out that there is a positive feedback of soil moisture on precipitation. So in the late phase volcanic eruptions, the accumulated soil moisture deficiencies before volcanism can lead to drier preconditions and less evaporations, which give rise to larger rainfall decreases after volcanism. However, in the early phase experiments, the dry preconditioning of soil moisture and its feedback on precipitation are weaker, so leading to smaller drought responses. These are my conclusions. Firstly, the Ming Dynasty map drought is initially triggered by internal variability in 1637 and then amplified by the eruption of Mountain Parker in 1641. The volcano intensified drought is associated with decreased land seasonal contrast and soil moisture and eastward retreating of the West Pacific subtropic high. Secondly, the response of drought to volcanic eruptions occurred at different drought phases are non-linear. If volcanoes erupt in the late phase of a drought, the drought will be longer and have larger intensity, and vice versa. This is contributed by positive soil moisture feedback on drought. And this also indicates that the Ming Dynasty map drought is more probably occurred in the late phase of a natural drought. These are my published papers, and that's all for my presentation. Thank you for listening.
Okay, great, thanks so much. Are there any questions? Let's see, hands raised here. Oh God. Yeah, I guess I had one quick one. So you mentioned that the volcanic eruption in the late stage of the drought is associated with the change in the subtropical high. Is there a systematic association with modes like ENSO or the PDO as well that you noticed?
Do you mean which internal variability triggered the map drought?
Yeah, I guess I'm wondering, do you think that the mechanism for the extension of the drought is atmospheric alone, or does it require coupling with the ocean in the sense that there's a phase shift of ENSO or the PDO?
We think that this drought was initially triggered by internal variability, and it is most likely the PDO will influence it. And then the PDO suppressed by volcanic eruption amplified its map drought.
Really interesting.
Thank you.
Okay, great. Thanks. If there are no other questions, I guess we can move on to the next speaker, who is Deepak Chandan. Are you here, Deepak? Hopefully.
Yes, I am here.
Perfect. Okay. Yes. Deepak will be speaking about land surface feedbacks and the Green Sahara.
Yeah, I can't share my screen while the other screen is shared. So.
Okay, fun. Could you shut off screen sharing, please? Thanks.
Okay, that's good. All right. You can see my screen now?
Go ahead.
Okay, great. Thank you. All right. Hi, I'm going to talk to you a little bit about Green Sahara termination today. This is work I'm doing with Dick Peltier at the University of Toronto. The work that I'm going to talk to you about is done as part of the SCRANE collaboration, which stands for the Computational Research in Ancient Near East. And it's a collaboration between archaeologists, anthropologists, computer scientists, climatologists to understand the climate of the at a time period when human civilization was just growing in the Near East. And its focus is on some very specific time periods where climate change has been invoked as significant external influence in those events, such as the onset of agriculture, genesis and collapse of urbanism, and then the collapse of Bronze Age civilizations. The idea is to perform a full transient simulation during these time periods and then do high resolution targeted modeling for some of these periods of interest. But the key issue is that during this time period, the climate was different in that region because of the presence of this thing called the Green Sahara. So we want to understand how the Green Sahara was and how it would influence our modeling approach. So the Green Sahara was a period of time when the Sahara was much greener than today. So it wasn't like this. It was inhabited by vegetation, and it had lots of lakes and wetlands and rivers, and it was inhabited by people and animals. And there's a lot of evidence for the presence of Green Sahara from all of these different lines that I've listed here. This Holocene Green Sahara was not the only Green Sahara out there. In fact, there have been many over at least the last 8 million years in response to changing orbital insolation. But I'm just going to focus on the most recent one, which is from just after the termination of the Younger Dryas till about 5.5 or 6 thousand years ago, which is our period of interest. So let me go back to this question about Green Sahara. And so, like I mentioned, we want to be able to do accurate climate modeling for some of these time periods to understand how climate would have impacted these civilizations, these societal changes. And so we want to understand the land surface boundary condition, which is the Green Sahara. And this question I'm going to break down into 3 different questions. How does the Green Sahara begin? How is the Green Sahara sustained? And how does the Green Sahara end? And I'm going to focus on this last part here, but let me just give you a brief introduction to the first 2 here. So how does the Green Sahara begin? We know now for a long time that the primary external influence was the rising solar insolation. And during this most recent Green Sahara and during this last interglacial. But over the past decade, interesting work has shown that while the rising insolation is important, there is a very important influence of millennial scale events in the North Atlantic that tend to synchronize the start of Green Sahara over Africa and control their spatial features. So millennial scale events are critically important. So in the last deglaciation, the Younger Dryas was one such millennial event. In the penultimate deglaciation, the Heinrich Stadium 11 was one such an event. And this is a figure from Meridional et al. That recently came out. How is the Green Sahara sustained? This has been a very important area of research, and over the last 40 years or so, a lot of work has been done in this regard, showing the influence of the feedbacks that are present from the land surface, such as feedback from vegetation, soil, surface water, feedback from the ocean itself, for example, that lead to the enhancement of the initial effect of higher summer insolation in the mid-Holocene. So this is a very dense area of research, and a lot of people have done very important work. But we published a paper on that 2 years ago, in which we talked about how the influence of land surface feedbacks that are currently known in the literature are not as strong as can be obtained in a modern general circulation model, mainly because some of the results are very old, and the models that were being used were very old, and the land surface boundary conditions that were incorporated in those modeling experiments were not very state of the art. So just to recap a quick result from this paper and to set the stage for the influence of feedback processes. Here I'm showing you on the left-hand side the enhancement to precipitation during the mid-Holocene that is obtained just from change and just from the higher summer insolation during the mid-Holocene. And you can see that there is some enhancement. And this here is the zonal mean of the precipitation, and that's the blue curve here. The black is the present day, and this is the anomaly. So you can see that there is some enhancement just in the tropics, but it's not enough, and it certainly doesn't cover the most of Africa, and it's not the magnitude is not high enough to agree with these proxies, which are shown here in circular markers. But then we try to incorporate the Green Sahara changes, and the way I do that is by changing the land surface conditions, such as the vegetation distribution, the presence of lakes, and the soil properties. So I'm just showing you here the changes to vegetation and lakes here. So in each grid cell in CLM, these are the dominant, currently for the present day, these are the dominant plant functional types, and I changed them to this thing here. In fact, in the changes that are prescribed, there are multiple plant functional types in each grid cell, just like there are in the present day as well. But I'm just showing you, instead of that 17-dimensional figure, I'm showing you just the dominant plant functional types. So I basically gotten rid of this deserted region here and incorporated and applied sort of a savanna / steppe type vegetation, and looked at the literature for the presence of ancient lakes that I've applied in the CLM model, and I've changed the soil color as well to change the properties of the soil, which would be expected to change based on the presence of higher organic matter and presence of moisture. So once I apply these changes to the model, then I have this new figure here for the mid-Holocene precipitation anomaly with respect to pre-industrial. You can see that the magnitude of precipitation increases considerably more, and then there's a lot of precipitation that extends deeper into the Sahara. The zonal mean here again is shown here. There are lots of simulations, but this is the result of including all the feedbacks together, and that's the green curve here. Shown here as anomaly, and they do agree pretty well with the proxies that are present for Africa, and you can see that agreement here in this figure, or you can see that agreement here in the top left figure, where I have collected the proxies in 5-degree latitude bands that are shown in the red markers, and the model inferred precipitation anomalies at those locations are shown in the squared markers. We do have a little bit of over prediction here. That tends to be the case for many models, but otherwise we're doing a pretty good job. So again, a modern coupled climate model can reconcile the available proxies simply on the basis of land surface feedbacks. And a key feature here is that the precipitation that we get here all over Africa is actually sufficient to maintain the vegetation that we prescribe, as opposed to what happened in some of the older studies where the vegetation that is prescribed leads to an improvement in precipitation, but the precipitation cannot actually sustain that vegetation. Okay, so this was about how to sustain a Green Sahara with land surface feedbacks, and there are other feedbacks as well that people have talked about in literature, such as dust feedbacks and feedbacks from the ocean. But now I'm going to talk about how Green Sahara ends, and just this is going to focus a little bit on the work that currently is in the review. And so the key feature of one of the interesting features on the termination of Green Sahara is this time transgressive termination, where several studies have shown that the Sahara terminates earlier in the north and earlier in the east. So there are various results over the years that have talked about this. This is one of the newer figures here, results from Shanahan et al. In Nature Geoscience. And based on this figure shows here the time of the onset of Green Sahara termination, and the markers are color coded according to this color bar here, and you can see that they sort of started earlier in the east and north, and there is a sort of, as you go westwards, southwards, they terminated later. Okay, so I try to understand that why this is happening, why this might be happening in the real system. So we found that this is the result of a feedback that arises from two different processes that are taking place. So the first one is the effect of change in the land surface. So if I have land surface that has an east to west difference. So actually I should have put something here. I forgot to put this thing, but let me just remind you that my land surface initially in the first paper was very zonally uniform changes, but this one I'm talking about when I do have an east to west asymmetry, so it's not zonally uniform. I forgot to put a figure here. I should have. So when there is an east-west difference in the amount of vegetation, this leads to an east-west difference in the simulated moisture that is available for this region. So these are all anomalies with respect to pre-industrial. So here I'm showing for the pre and mid-Holocene. So it's wetter on the west and it's drier in the east. And I do the same thing for the early Holocene, which here is 9 Ka. And in early Holocene as well, with everything else being the same, you see that again there is a response where the west is slightly wetter and the east is drier. But the response is actually weaker in the early Holocene than the mid Holocene. So this influence of difference in the east-west vegetation is actually more important in the mid Holocene and is weaker in the early Holocene. So the key fact is that this is important during the waning phase of the Green Sahara, not in the early phase when Green Sahara was more prolific. So that's one thing to keep in mind. The second thing to keep in mind is the effect of change in so the reason why this happens is because there is this land surface change leads to an anomalous upper tropospheric change in the water circulation. You have an anomalous ascent in the west, which leads to more convective precipitation, and you have descent over the eastern part of Sahara, which leads to drying. So the second effect is the effect from the change in insolation. So here I'm showing you these three figures that are all mid-Holocene minus early Holocene. But what is different between each of these is the vegetation that has been prescribed on the surface. So if we have only pre-industrial vegetation, then going from the early Holocene to the mid-Holocene leads to a uniform drying all across Africa. But if you have a Green Sahara vegetation, then depending on the characteristic of the Green Sahara vegetation, there are two of these here I'm showing. What you do get is a little bit more preferential drying in the east and either stationary conditions or wetter conditions in the west. Okay. So the presence of Green Sahara interacts with the changing Holocene to lead to this kind of response, which is also mediated through a change in the water circulation above this region. And that is shown here. So if you have in the reference case where I'm only having PI vegetation, 1 minute warning, right? Okay. Yeah. Mm-hmm. I'm just going to wrap up here. There's this continuous descent over Sahara, but when you have a mid-Holocene, a Green Sahara simulation, then you have a change in the water circulation that leads to this difference. So those two effects, the change in insolation leads to a change in the ground surface, and the change in the east-west greening then itself leads to a change in the precipitation response, leads to a total response that is that is shown here on the right. Okay, so you have more drying in the east, and you have actually a greater amount of precipitation in the west between early Holocene and mid-Holocene. So what this does is that coming up from 9 Ka to 6 Ka, your desertification would have started in the east, but it would have been effectively delayed in the east here. And the key impact is that this feedback actually weakens later in the Holocene. So if we look at the around 3 Ka versus mid-Holocene, then after mid-Holocene, this desertification continues in a zonally uniform way. which is exactly what we observe in proxies. We observe that the onset, there's a difference in onset for some time, and then later in the desertification process, proceeds in a zonally uniform way. Okay, so quickly, just very simple summaries. Land surface feedbacks are important to sustaining Green Sahara, but they are also important during determination of the Green Sahara. And it's the interaction of the land surface with the changing insolation during mid-Holocene that delays desertification in the West, and the onset of desertification in the West, I should say. Okay, so I will yield there.
Great, yeah, thanks so much. Anyone have any questions? Okay, well, yeah, I think we do need to move on, unfortunately, in the interest of time. But again, please feel free to put questions in the chat if you do think of anything. Yeah, super interesting again. All right, so I guess our next speaker is Theodore Meyer. Theodore, are you here? Yes, perfect. We'll be speaking about water isotopic imprints on the Pacific Walker circulation. So yeah, take it away.
Yeah, great, thank you. Can anyone see my slides?
You're good.
So yeah, welcome. My name is. I'm excited to share some of my Pliocene research. I will talk about the hydrological imprints on the Pliocene Pacific rock circulation. Knowledge. My advice Ran Feng, which talk you heard.
Sorry, I'm having a little bit of trouble hearing you. I don't know if others are as well. It sounds like there's maybe some background noise or interference.
Okay, just 1 second. So I hope this works better.
Yeah. Seems
okay.
to be. Yes, go ahead.
So yeah, I'm going to talk about the Pliocene Pacific rock circulation. And just to give some background, the Pacific rock circulation is a model of airflow in the tropical Pacific and is characterized by the rising air masses over the West Pacific warm pool and substance in the east. And understanding how this circulation is changing to respond to the response of current and future climate to CO2 increase is important, as it has been shown that changes influence the global warming potential and tropical hydroclimate patterns greatly. And one of the key predictions of global circulation climate models is the weakening of this circulation. However, instrumental observations over the past few decades have been inconsistent and do not support this clear signal. And reasons might be strong internal variability and anthropogenic aerosol forcings, which makes analysis more difficult. But nevertheless, it's very it's apparent that there's a need for new and model prediction assessment. And for that, we propose to use the water isotopologue archive of the Equatorial Pacific. So why I'm looking at the water isotopologue? Well, recent research has shown that there exists a strong linkage between the circulation and precipitation pattern changes. For example, this left figure from Chang et al., where you can see the strong correlation between the vertical velocity and precipitation of the last few decades. And other research from D et al. On the right here, which as we can see clear isotopic difference between Eastern and Western Pacific during different Pacific rock circulation states like the El Nino and the La Nina conditions. The isotopic composition depends on the incoming moisture from different regions and also phase change processes, and all these combined effects get influenced by changing of Pacific rock circulation. So these first results here show that there's an international timescale that changing circulation is imparting some sort of signal to the isotopic record, and the hope is that over longer timescales, the hydroclimate signatures can be used as a proxy for CO2-induced Pacific rock circulation change. And for that, I'm looking at the late Pliocene as a climate analog. This time it will have similar geography and vegetation to today. as further characterized by the mid-Pensensian warm period with elevated CO2 concentrations and the subsequent decline, which led to the intonation of major Northern Hemisphere glaciation, as you can see here, the black bar. And because of the possibility of obtaining leaf wax deuterium records through my collaborators, I'm currently, like all the figures you see here, are focusing on simulated precipitation deuterium record and its connection with the circulation strength changes. For my experiment, I used Community System Model version 1.2 with isotope tracking enabled. This allows for the tagging of water and water isotope logs, originating from user-defined regions throughout the rainfall and transport history. And it's also important to note that I'm using a mixed layer ocean component with simplified heat physics. And in total, I did 4 simulation sets with 1, 1.4, 2, and 3 times CO2 from the pre-industrial, for pre-industrial and Pliocene bounding conditions each. So let me show you some of the first connections I've found so far. So here, that's a precipitation change for a doubling of CO2 in the Pliocene and Pacific. As you can see, the Pacific rock circulation weakens as expected, and this results in increase in precipitation, especially in the eastern equatorial Pacific. And if we look at the deuterium pattern on the first order, the change matches the precipitation pattern. We have like a west and eastern side, and here I draw these boxes, which are the west equatorial Pacific and the east equatorial Pacific. And for my next slide, I'm going to use like these averages from these boxes to compare the 2 sides better. So that's what we get. On the left red axis is the east equatorial Pacific, and the blue right axis the western side. And we have 2 figures for the pre-industrial and Pliocene bounding conditions. And as you can see, as the CO2 increases on the x-axis, we have an increase or like an enrichment of the deuterium on both sides of the Pacific. And this can be explained by the weaker fractionation, higher temperature. So it's a direct warming response of the hydroclimate pattern. The rate of enrichment is lesser in the east compared to the west, as seen by the closing in of the red and blue points, right? So the difference getting smaller and smaller. And this signals is apparent in both pre-industrial and Pliocene, so that means the boundary conditions doesn't have a large influence. Now here I looked at the decreasing difference between east and west we've just seen, and that correlates pretty well with the weakening of Pacific rock circulation as CO2 increases. So again, the left we have the difference term, and on the x-axis the mass overturning, which are used as a direct measure of circulation strength, which I calculate from the top right equation up here. So that's very promising. We can see like, okay, at least for like larger CO2 changes, we can see some the deuterium change, which might be useful for Pacific rock strength proxy, right? The difference between the east and the western Pacific might be useful for that. And just for completeness sake, this is the solar mass stream function, which I used over the Pacific. The mass overturning is in the middle here, the red, and the wind is following the contours. So now for the next part, I just want to delve deeper in the mechanism of this linkage by utilizing the water tracking. And I want to know if we can understand like the changes the deuterium is coming from. I'm only like going to scratch the surface here. It's just some first looks at it, but we can also do some interesting stuff. So the water tracking, as I mentioned before, allows to track water throughout the hydrological transport. And we look at the Western Equatorial Pacific again as sink regions, and I'm only looking at the moisture recycling this time. So here we see the change of fractional precipitation from West and East Pacific, and it's partitioned into local recycled precipitation from the region itself, and the remote moisture from the rest of the world. And despite the absolute increase to the warming, there's a reduction in the locally sourced relative precipitation at both sides of the Pacific, right? And this is compensated by the increase from remote regions. This means The enhanced precipitation is more driven by moisture convergence than local convection. And the switch in precipitation is especially pronounced in the East Equatorial Pacific. This is very interesting because remote sources are more like colder and thus more depleted in deuterium, or like are there any isotopes? And we think that the increase in remote moisture is muting the normal enrichment rate. And because the effects large in the east, we have this low rate of deuterium enrichment we have seen before compared to the west. So that's just kind of one outlook why it changed. So in conclusion, I showed that the contrast between recent equatorial Pacific water isotope could be useful for Pacific range proxy, and that the isotope rate difference is linked to varying rates of moisture conversion change at East and West equatorial Pacific. And for my future and ongoing work, right now I'm working on coupled simulations and proxy data comparison, and in future I will expand my research by including ocean state proxy and the impact of early Pleistocene glaciation expansion on the Pacific water circulation. Yeah, thank you. That was my talk, and if you have any questions.
Okay, great, thanks. Yeah, and we do have a minute for questions. You're very concise. Anyone? Yeah, I guess, yeah, this is really interesting. And so I guess I wondered, do you see similar patterns in the delta 18O precip? Do they correspond very well to delta D? Or?
Yeah, yeah, more or less.
More or less, okay.
Yeah, we're looking at more delta 18 now. Sorry.
Yeah, super cool. All right, well, yeah, we are a little bit behind the schedule, so I guess we can move on to the next speaker, who is Mary Grace Albright. Are you here?
Yes.
It's speaking on the mid-Pliocene North American monsoon and weather-resolving coupled simulations. So please share your screen and yeah, take it away.
All right, everyone see my screen? Okay, perfect. Okay, all right. Hi, everyone. My name is Mary Grace Albright, and I am just finishing up my first year as a PhD student at the University of Connecticut. And I'm working with Ran Fing on a project called Mid-Pliocene North American Monsoon and Weather Resolving Coupled Simulations. So first, I wanted to just start by giving some background information on the mid-Pliocene and point out just a few important features that are here. So we are studying the Pliocene to see how the North American monsoon could potentially change in the future. So not only did it have similar topography and bathymetry to our current Earth, but it was also the last time that it saw an atmospheric CO2 level that's similar to present day, so around 400 ppm. And our estimates of warming here, which you can see here in the chart where the y-axis is change in temperature in relation to pre-industrial, they were about 1.8 to 3.6 degrees warmer than pre-industrial, which you can see about right here. And these temperatures are similar to predicted warming in the future based on intermediate warming scenarios, which is highlighted here in the light blue. And so the North American monsoon itself is an atmospheric circulation feature of hydroclimate in the North American Southwest. So it starts to develop in Mexico in June and then moves up into the US Southwest in July until about mid-September. And the North American Southwest really depends on its rainfall as a source of water, with Mexico alone receiving upwards of 75% of its average annual precipitation during this monsoon season. So this means that future changes would have a really big impact on the people living here, which makes it all the more important for us to understand how it might change going forward. And now, the North American monsoon was traditionally thought to be thermally forced, where the land and mountains heat up quickly during the summer, creating low pressure and moisture convergence towards the land and high topography. However, more recently, a new study by Booz and Pascal demonstrated that the mechanical forcing by the Sierra Madre Occidental Mountains is perhaps more important than a thermal forcing here. So they did this by running two different simulations, one with modern orography present and one with flattened orography. And we can see that in the figures down here. So the one with the orography present has a clear band of summer precipitation in our monsoon region that we're concerned about. And the red contours are near surface eastward wind. So here we have the wind converging, pulling air up. And with the mountains, there's moisture convergence to the western side, which leads to locally enhanced precipitation formation. Meanwhile, in the simulation with the flattened orography, there's essentially no monsoon ring band in our region that we're concerned about, and the wind contours stay to the north and south here. Now, within these simulations, high horizontal resolution is really important for capturing some of the key features of this monsoon. So these right here are two of the same models run at different resolutions. So you can see in the low resolution, the ring band is really poorly defined, and you can only really start to see the clear North American monsoon ring dependency on topography in the high resolution simulations. Now, also within these simulations, the North American monsoon is predicted to weaken in response to future warming. So there is general model agreement of drying in the North American Southwest, which we can see in this figure on the left, where the red box is highlighting our Southwest North American region. And so this is showing us a precipitation decrease of 10 to 40% for the end of the 21st century. And this drying only increases in magnitude over time as a function of the strength of radiative forcing. However, this agreement is not necessarily shown in all proxy records for the Pliocene. So this figure on the right here is showing us a Southwest North American proxy reconstruction where this gray band is the mid-Pliocene. So I wanted to highlight the middle trend line, which is showing a more enriched delta D signal for precipitation, which could be indicative of an increase in warm season precipitation or tropical storms in relation to today. So one of the framing questions of our work here is whether we can use high resolution simulations to start to bridge this gap between model results and proxy data. And so to do this, we use CESM 1.3 with the spectral element dynamical core for the atmospheric component. Then for sea ice, we use Community Ice Code version 4. For ocean, we use Parallel Ocean Program version 2. And for land, we use Community Land Model version 4. And for comparison purposes, we ran this model in two different resolutions, both run on a cube sphere. So they both use the typical 100-kilometer resolution for ocean and sea ice, but the high resolution model used a resolution of NE 120 in the atmosphere and land, which regrids to about 25-kilometer lat long. And the low resolution used NE 30, which comes out to be 100-kilometer lat long. And our motivation behind these resolution choices were because most models are run at or above 100 kilometer. And at this scale, you're only going to be able to resolve things like large mountains, fronts, large scale cyclones, etc. Below this scale, though, at roughly 25 kilometer, we can start to resolve things like small mountains, land sea breeze, and organized mesoscale systems. Now, when we set up our high resolution simulations, our boundary conditions came from PRISM 4D, which maps to the high resolution topography and bathymetry. And the initial conditions for ocean, ice, land, and terrestrial carbon cycle come from a 1,200-year long simulation from a previous mid-Pliocene run. And the only part that was initialized from code was the atmosphere. And this initialization allowed for a pretty short spin-up time where our high resolution experiment equilibrated within about the first 5 years. So we have initial diagnosis for the first 30 years, here the TOA radiation imbalance, and we do actually have 45 years of the high-res run now, and we're planning to ultimately extend this to 70 years. Now, first, I'm going to show the added benefit of high resolution to the mean climate state by just looking at our pre-industrial simulations. So we use the last 50 years of our low resolution runs to compare to the last 30 years of our high resolution runs. Now, first looking at the difference in elevation, we can see that in the high resolution, the mountain range sits at a higher elevation and is much more confined to the western side of Mexico. Meanwhile, in the low resolution, this mountain belt is more diffusive and it covers a wider area. And so what this means for summer precipitation is that in the high resolution, this core monsoon band is more narrowly defined to the western side of the mountains than in the low resolution. And in this low resolution, the band is more diffusive and it runs across the mountains. And we think that this difference relates to the enhanced topographic gradient, which would cause greater upslope compression and limit the amount of precipitation that's developing in the high resolution simulations. So now I'll show the comparison between the Pliocene and pre-industrial data that we have. So the one thing that I do want to point out before we move on is that because of our boundary conditions that were based on the PRISM 4D reconstruction, this mountain range does actually sit at a lower elevation in the Pliocene than in the pre-industrial, which we can see in these figures up here. And this difference plot down here, where everything in the blue sits lower in the Pliocene. And this difference in the high resolution is the same as the difference in the low resolution. And this would be because of the geodynamic model by Dowsett et al. In 2016, which runs to adjust topography on Earth due to the loss of Greenland and West Antarctic ice sheets. So we can see that in their reconstruction right here, where this is our North American Southwest region and the blue is our lowered mountain range. And so in terms of what this means for the annual precipitation differences, we can see consistent bands of drying in both of these resolutions. And we can see that the lowered elevation in the Pliocene leads to anticyclonic circulation at 850 millibar forming in front of the mountain in both resolutions. So this takes precipitation away from the region, resulting in drying to the western side of the mountain. And we said that this would be due to the lowered mechanical forcing, which is consistent with results by Booz and Pascal from 2021 that I talked about in the beginning. However, we then look at early summer precipitation changes. There is actually more of an enhancement of the eastern monsoon rain belt and the high resolution run. And these findings are consistent with the proxy evidence that I also talked about earlier of the wetter rather than drier conditions during the mid-Pliocene in this region. And so the question that we're asking now is whether these differences are possibly due to the presence of mesoscale convective systems, which can only really be detected in the higher resolutions. And so to track these features in our simulations, we use an algorithm called tempest extremes. So this works by first detecting intense precipitation events, which would be similar to these green blobs forming here. And then it determines if these events are propagating features, which you can see in the pattern of the animation. And this detection is determined by hourly precipitation thresholds. So we used a Monte Carlo search guided by root mean square error to determine which parameters gave us the best results. And these were the parameters that we got from the search. So the precipitation threshold was set to be about 2.15 millimeter per hour. The minimum size for an event to be considered had to be at least 4,500 square kilometer. There was a 0.7 degree radius of smoothing, which essentially determined the influence of a cell on its neighbors. And then the event had to persist for a minimum of 2 hours, and there could only be a minimum of 10% and a maximum of 10% or a maximum of 60% of overlap of the area of the event from one time step to the next. And as we can see in these figures on the right, our track storms are in general agreement with the observational data for a historical time period. So in the US, the central Great Plains were especially difficult to match. And we've seen better results in non-hydrostatic simulations. So we think that perhaps the non-hydrostatic balance is important to capturing the mesoscale convective system distribution of this area. However, for the North American monsoon region and Southern Asia, these results showed a pretty good match with observation-derived mesoscale convective system numbers. But we're also working on applying our parameter sets with ERA data to check if our model parameters can reproduce realistic MCS counts from observations. And since our models are hydrostatically balanced, it's possible that they might not be capturing enough intense precipitation, which means that we might need different thresholds. But once we did run this algorithm on the Pliocene and pre-industrial, we can see that in these figures here that there is an overall increase in MCS frequency in the northern side of the monsoon region, where we previously saw enhanced precipitation during the Pliocene. So this northernmost area right here. And here in these figures, we see precipitation that is just being brought by mesoscale convective systems. And this is showing us that they are bringing more precipitation in the same area as the last figure, so right here. And we think that this likely helps to explain the greater mean precipitation in the high-res than the low-res simulations, because the low resolution are too coarse to capture these atmospheric features. So to conclude, we saw that there were substantial differences in the monsoon state in the pre-industrial simulation that can be attributed to better resolved topography. And we also saw that the mid-Pliocene annual precipitation was controlled by the elevation of the Sierra Madre Occidental mountain range. And then in the high resolution, there was an enhanced eastern monsoon rain belt in the mid-Pliocene early summer precipitation. And lastly, we saw that preliminary results suggest the increase in summer precipitation is associated with an increase in mesoscale convective system frequency. And now, just some future directions that we're planning on taking. We are planning on quantifying differences in storm occurrences and precipitation that's attributable to these storms. And then we're planning on running a version of the high resolution code with 10-kilometer resolution ocean sea ice instead of our previous 100-kilometer, which has not yet been exported for paleoclimate. And then we're also planning on looking at water isotopes, high-res simulations once these become available. And then lastly, in addition to tempest extremes, we are also planning on trying ClimateNet to see if we can use a deep learning model for pixel level identification or segmentation, rather than a threshold-based model to track some of this extreme weather. So here are just some funding acknowledgements, and I wanted to thank you all for listening to my talk.
Great, thanks. Another great talk. Any questions, please? I had one super quick one. I guess I was curious about your preliminary MCS results. Do you see, is that increase an overall increase, or is there a systematic change in the seasonality, or do you not know?
Hold on one second, let me reshare.
Okay.
Okay. You're talking about here? Oh, sorry. I forgot to mention, this was June through July mesoscale convective system counts. So this is the same time period that we saw an increase in precipitation right here. Does that answer your question?
Yeah, it's not super important, but yeah, it's really, I guess there's I just, you could get changes in the like peak season of the monsoon, which might matter. So I was curious about that.
Okay, yes. Yeah, I did look at like the full summer mesoscale convective system differences, and we did also see, hold on, looking at it again. We did also see an increase in the same region, but it was more pronounced in early summer.
Cool. Yeah, Julio has a hand up.
Yeah, thanks. That was very interesting. I'm wondering, can you tell from tempest extremes whether you're seeing an MCS or a tropical cyclone?
Yeah, so there's different ways of tracking tropical cyclones versus mesoscale convective systems in tempest extremes. So this one was specifically for looking at mesoscale convective systems. So it works as like tracking like blobs. So it first like detects the blob, then figures out if it's a propagating blob. And then there's like a different part of the algorithm that you can use for tropical cyclones specifically.
I'm just wondering, if you're tracking a precip blob, it might not know that it's a tropical cyclones have a lot of precip too.
Yeah.
You exclude, okay. I was just wondering if you explicitly exclude tropical cyclones in some way.
I don't think it specifically excludes tropical cyclones, but we have planned on looking at tropical cyclones in addition to mesoscale convective systems and seeing how those results compare.
Okay, thanks.
Yeah, super interesting. Okay, I think we probably have to move on. I know there's at least one question in the chat. We can continue the discussion there, but I did want to give poor Yunta, who's been so patient, a chance to finally present their talk. Are you still around?
Yeah.
All right, perfect.
Yeah, thank
so
you.
Yeah, go right ahead. We will hear all about tropical South American precipitation during the last deglaciation.
Yeah. Yeah, can you hear me clearly?
Yep, yeah, you're good.
Okay. So, Yeah. Hello everyone. I'm very glad to join the Paleoclimate CESM workshop, and I am Yuntao Bao, a third-year PhD candidate from the Ohio State University. And during the past 2 years, we mainly focused on the millennial scale variability of tropical South American monsoon system. And today I will present the results from the results from the studies, the dipole response of millennial variability in tropical South American hydroclimate during the last deglaciation. As we have more and more instrumental observations and cave speleism data, one can study the different times, the South American summer monsoon variability on different timescales, and the most studied one is the interannual timescales. Like this figure shows the precipitation response to ENSO variability to ENSO, and you can see interesting that the precipitation response is not a spatially coherent change, but there is an obvious dipole response with contrast change between the west central Amazon and the eastern coastal Brazil. And it's also interesting to see that in a very longer time scale, the orbital time scale, we can also see a similar dipole response in both data 18 reconstructed from speleism site and also the snapshot climate model simulations. They both show a clear dipole west and east dipole response in both precipitation and data 18. But for millennial timescale, things seems to have changed. With available speleism data over the tropical South American, most previous studies show that there is a coherent variability of millennial variability of data 18 over these sites. And if we look closely to the right figure within the last 25,000 years, it's very clear that they show a coherent variability of data 18. And we can also see that at the HS1, Henrik stage 1, there is much more depleted data 18, which shows wet climate conditions. And based on this, previous work conclude that at the HS1, the South American summer monsoon system increased. So that's the short conclusion that based on available speleism records, the millennial precipitation variability across tropical South America has a very large coherent pattern. It is, if you recall that we mentioned in interannual and orbital timescales, there is a dipole response of precipitation and data 18, but for millennial scale, this dipole seems to disappear. It is very weird, right? But if we note that the location of these sites, most of them located in the eastern coastal Brazil region, and some of them at the western Amazon and Andes region, little of them located in the inland Amazon region. So we would question this, the conclusion of this coherent variation. If we get more more paleo proxies, will the conclusion change? Yeah, so this is our research question, whether there is a robust continental scale dipole in millennial precipitation and data 18 over the tropical South America. If so, what's the mechanism that induces such a large scale dipole response of the millennial hydroclimate variability? And if there is a dynamically robust dipole response in precipitation and data 18, what is the proper index for the South American summer monsoon system? And how does this system respond to meltwater forcing? So to answer these questions, we did 3 parts of work. Firstly, we will do the model proxy data comparison to validate the performance of our simulation. And the second part is to investigate the mechanism of millennial rainfall response. And the third part is the mechanism of millennial data weighting response. Okay, so firstly, let us look at the model proxy data comparison. So as this figure show, again, most of the available speleosome cave data that is available to study the millennial variability during elastic glaciation concentrated in these coastal regions. Only one also is in Amazon region. Since the ICSM model is enabled the water isotopes, so we can directly compare the reconstructed proxy calcite data weighting with our model calcite data weighting. So the black line is for proxy and the green line is for the model. So you can see that all of these eastern coastal sites, our model can capture a very good variability of calcite data weighting compared with the proxy data. But one thing is that model tend to underestimate the magnitude of the millennial variability. The reason for this, we don't know yet now, and we will continue to study that in the future. So since the model is validated, we think it's okay to study the mechanisms of millennial rainfall variability over the tropical South America. So as we mentioned before, due to the spatial coverage, limited spatial coverage of the proxy data, we cannot capture the complete spatial temporal variability of tropical South American monsoon. But with this ICSM model, we can do that. And firstly, we perform the combined EOF of precipitation and data weighting. And this figure shows the leading mode of the CEOF. And you can see that the PC1 time series, the black line, shows a very clear millennial scale variability. And combined with the blue line, that is the AMOC intensity, they tend to follow each other, which means that the leading mode is the millennial scale hydroclimate variability over the tropical South America, and is mainly driven by the AMOC intensity, which is driven by the North Atlantic meltwater forcing. So if we look at the spatial pattern of this CEOF mode, we can see a very clear dipole response, right? The contrast change of precipitation and data weighting between the Western and Mid Amazon and Eastern Coast Brazil. Yeah, so, and our model results is also consistent. By the way, it is the transient model simulation. Our model simulation is also consistent with the snapshot model simulation by campus in 2019, which shows the precipitation difference between HS1 and LGM. You see that they both have the similar dipole precipitation pattern. So another question we want to know is that how will the South American summer monsoon intensity change at the HS1 or younger Dryas due to the increased meltwater forcing? So like the figure E and F shown, the increased meltwater forcing produces the ITCZ shift southward, and this produces an anomalous ascending motion in coastal Brazil, but anomalous descending motion in west central Amazon region. And it is also associated with an anomalous cyclone on the upper troposphere, which decrease the climatology Bolivia high. And in the lower troposphere, we can see there is an anomalous westerlies, which decrease the climatology low level westerly. So based on this atmospheric circulation anomalies, we conclude that the South American summer monsoon intensity should be decreased at HS1 and younger Dryas. This is contrary to the conclusion in previous studies. And the reason of that, again, comes to the previous argument that they only have the proxies concentrated in the eastern Brazil part. So they do not capture the whole spatial pattern of the South American summer monsoon variability. Yeah, so the next part is the mechanism of millennial data weighting over the tropical South American region. So starting from 1964, Stenshgard pointed out that the tropical data weighting mainly represents the local rainfall amount effect, and this is widely accepted by paleoclimate communities, and they also think that the change of data weighting over the tropical South American also represents the local change of precipitation amount. But here, in our model, in millennial timescale simulations, we can also see this pattern, like the increased precipitation is associated with depleted data weighting. Seems like, yeah, it's the amount effect dominant, but later we will show that the data weighting change cannot indicate the local rainfall change. It's also out of our expectation. So to investigate the mechanisms of data weighting, we did the water tagging technique. That is, we tagged the source region 016, water 016 and 018 from the evaporation of ocean or land region, and they become the water vapor, and then they go inland into the land region, and from the source region to the sink region, the difference is called the upstream inroad of the vapor. And at the sink region, since the water vapor condensed to the precipitation and rain out, we call this local process the condensate change. Okay, so that's for water tagging. So firstly, let's look at the tagged moisture source. Because if you can recall, we have the dipole response, the Western Central Amazon and the Eastern Brazil. For the Western Amazon, the most precipitation moisture is from the equatorial Atlantic Ocean. But in contrast, for the Brazil region, coastal Brazil region, the moisture is mainly from the subtropical South Atlantic region. And another interesting source is the land South American continent, which means there is a very strong moisture cycling here. And to investigate the mechanism of the data weighting change, we can just take the difference between the total data weighting in precipitation between HS1 and LGM. And this can be, this total change can be further decomposed into the data weighting composition and the relative moisture source contribution. And so let's first look at this right panel. It shows that the total data weighting.
This is your 1 minute warning.
Okay,
that would be great. Thanks.
I'll be quicker. Yeah, thanks. So you will see that the total data weighting change between HS1 and LGM, the dipole pattern, is mainly dominated by the relative source moisture contribution. This means that I will give you an example that like in Eastern Brazil, in LGM, the blue line, the large contribution of moisture is from South Atlantic Ocean, but at the HS1, the red bar, the moisture contribution from equator region increased a lot. So that causes this relative source contribution change and causes this dipole response that depleted in Brazil and enriched in central Amazon. And this dipole pattern is also enlarged by the delta weighting composition. And the delta weighting composition, as we said before, can be further decomposited from the source region, upstream rainout, and local condensation change. And this is mainly dominated by local condensation change. And due to the time limitation, I only give you the we only give you the result that we find this condensation change is mainly produced by the increased rainfall evaporation. So yeah, causes this change. So yeah, that's all for my presentation. So in our study, we mainly focus on the variability, millennial variability of tropical South American summer monsoon, and they are tightly connected to the ITCZ shift, southward ITCZ shift, and yeah, and connected to the atmospheric circulation, which combine together to produce this dipole response of both precipitation and delta weighting. Yeah, that's all for my presentation. Thank you.
Okay, great. Thanks so much. Yay. All right. So unfortunately, I don't think we'd have time for questions, but again, there's always the chat. Okay, so I think our schedule had us taking a break for the past 10 minutes and coming back at 12:20. So just as a suggestion, you want to take a 5-minute break and reconvene and start again with our CSL discussion? Does that sound reasonable, John?
Yeah, I think so. Let's maybe take a 5 minutes break. And I want to remind the speakers, please send your slides to Elizabeth if you want to have them posted on the workshop web page. So maybe we reconvene at 12:23 maybe.
Sounds good.
And
yeah,
for later, yeah, we will have a general discussion and then a special discussion on the CSL proposal. And it's supposed to be informal and that people can have a chat over lunch if you like. Thank you, everyone. And thank you very much for the speakers. Exciting talks. Thank you.
Jean, I have an updated slide which I can share.
Okay. Thank you.
Mm-hmm. John, what time are people coming back? I can update the slide to reflect that.
Oh, 12:23.
12:23, so soon, okay.
Yeah. Okay, maybe we get started with our discussion. Thank you everyone for people who stayed. And I will share my screen. Okay, to guide the discussion. So I guess first, maybe we can have a short general discussion, could be on the presentation this morning or on other related topics. And then we can move on to a discussion on the CSL proposal. And another quick question right now, we are still recorded. I'm wondering, how do people feel? If you think it's better, it's more casual if we turn off the recording, it's also fine. Just let me know your preferences.
Should I start asking questions?
Sure, go ahead.
I have a question for, excuse me, for Tomasz. Is Tomasz still here?
Yes, I'm here.
Yeah, I was surprised to see the model proxy comparison with sea surface temperature is so bad compared to the model proxy comparison for carbonate 018. I was wondering if whether this result also applies to if you only look at model proxy SST comparison for the SSTs that derive from 018.
Well, it kind of depends in a way. What do I transfer, or what do I model, if you will? Because I was showing data 18 on calcite.
Mm-hmm.
That, of course, the model does not compute. So I calculated that from delta 18O of seawater, and then used a transfer in order to get to the delta 18 in calcite. And for that calculation, I used the temperature, of course, the sea surface temperature, and apparently it's kind of strongly dependent on that. And that the dependence from latitude, the model gets quite well in the surface temperature, and that's why I had a little feeling that perhaps it was, yeah, how to say. So I'm not sure whether I can 100% trust that, to be honest. So one part of this conversion is a bit fishy indeed, because it's a discrepancy that the sea surface temperature matches much less than what the delta 18O does.
Mm-hmm. Yeah, I was wondering, so are those sea surface temperature all from calcite? My understanding they're from a variety of sources. I guess my question is more like, if you pick up the sea surface temperature from calcite, just do that comparison, while the model proxy data comparison better than what it looks like now?
Yeah, from the top of my head, I don't know, but I should check that. That sounds curious.
Cool, thank you.
Yeah, thanks.
Maybe I can add a related comment. So there are multiple SST synthesis products, and the comparison also depends on which product you use. And I think there are differences. Some products, the LGM sea surface temperature is colder.
Yeah, maybe I can just very quickly for a second show an additional slide for that, if that's okay here, that I did not show in the presentation. So yeah, depending, of course, which what data set you compare it to. So this is an extended table from what I showed, and if you compare it to most of them are smaller, but you also find published values that are a lot larger. For example, from Tieneta recently with ICSM. So that is a much closer match to those. I picked the most recent one from reconstructed data, that was also compiled within Palmetto, and for that, the VSM was a better match. But yeah, so it's pretty broad. I mean, it's after all these years, it's still not sure, especially the lower latitudes, what was the LGM anomaly. So whether that was actually a slight warming or a slight cooling, it's not. We don't know for sure.
Can I ask a question to Pedro? Pedro, are you there?
I'm here.
You showed several simulations from the water hosting. So what's your thoughts on this? So do we need to add more water hosting simulations, or do you think the community need a water hosting map, something like that?
Thanks for the great leading questions of things I'm interested. Let me think about it. I think we need more models, probably sampling the uncertainty with freshwater forcing rates or locations really doesn't matter as long as the AMOC weakens. That would be my conclusion. But if you look at our ensemble, is a lot of simulations, but they're run with fewer models. We probably have 7 different models, and 3 of them are NCAL models, CSM 3, 4, and 5, and CSM 1. So I think given that the uncertainty that we find, at least for the tropical response, seems to be the structural problem in the models, that's our main hypothesis. There is something that the models do that some cool the tropical Atlantics and others don't, because when you look at the agreement, it goes by families of models, right? The MIROC model cannot cool the tropical Atlantic no matter how you force it. And the ENCA models tend to. So I think we need more models and to be able to get more of those responses. But having said that, I have a hunch that the glacial boundary conditions probably matter for that connection between the tropical Atlantic and the high latitude North Atlantic to propagate that cooling. I have a feeling that the ice sheets are important. But I'm not gonna be asking to run, the different LGM simulations and then host them. That would be expensive, but it's something to think about if we want to be more systematic about that. So I think we need to buy more models too, but it's difficult, right? Because you need an LGM simulation, which are expensive, and not every modeling center can do glacial simulation. So you're kind of stuck in there. I wonder what other people think about that.
I mean, I think we're going to have trouble actually getting to the point of making statements about which model physical differences are important for these types of things unless we've run simulations with all of these different models. So yeah, I tend to agree. But how to do it is another challenge, right?
Yeah, probably we need more research, and we plan to do it, understanding this connection. It seems like it's a structural issue in models. You can see it for the AMO. There's a paper by Martin and others that shows that even if you look at the modern day AMO in pre-industrial runs, models also separate into two groups. So, yeah.
I was just curious on that point. Is this model physics and dynamics, or how important is resolution? And could maybe we do something where we had lower resolution versions where we could run more of these type of sensitivity experiments and still get the same response?
It's a good question, Clay. I don't think it's resolution, because some of these models do it, right? So, and they're all pretty coarse. We only had one degree resolution atmosphere. All others were less coarser than that. It's something in the West feedback, the way it's excited by the changes in the mean latitudes. And again, I don't know exactly what's going on in the models, but you saw it that the same thing happens for greenhouse gas warming. And there's a bit of a match. If a model does it for the past, it also does it for the future, or it doesn't do it. So it's something more fundamental. And I don't know what it is.
I want to circle back to the points Pedro raised regarding the ice sheet forcing. So in particular for the CESM model family, the LGM simulation and some slice simulation, usually we use the ICE6G, ICE5G. And in this morning, we saw quite a few talks from, especially from the Palmetto group. Looks like they use the terrace of ice sheet reconstruction in their studies. I'm wondering we can have some added value of if we explore this uncertainty from the ice sheet boundary condition.
Yeah, we have that ice sheet in one simulation that you then share with us. Our CCSM4 simulation has that ice sheet.
Okay.
And then my CSM1 simulations have ICE G6, and then all the other ones have 5. And so it might play a role, but probably the small differences don't matter. Maybe the changes in the mean state are the ones that matter. But again, we need to do more research on figuring out that specific how that mechanism is triggered.
Yeah, I think even from the global temperature response, this perspective, if you use a different ice sheet reconstruction, in the end, the effective forcing could be slightly different. And when you consider that the ice sheet topography can change the wind fields, then that can impact the clouds, then the effective forcing could be amplified. So I think something may be worth exploring.
You're still talking about static ice sheet forcing, right? Like we haven't even gotten to dynamic ice sheet coupling yet.
Yeah.
Yeah, I think we should look more into that. Actually, my hosting simulations are not ICE G6, are PMIP3. So there's no hosting simulation with that ice sheet in this ensemble.
Okay.
So we should host our LGM that has ICE G6 and see if we see a difference.
People have other questions or comments?
It's like if we're talking about kind of big picture uncertainties, particularly like, you know, to set up maybe like use of CSL allocation resources, then it seems like ice coupling is one, or, you know, water hosing sensitivities, but also I think the resolution thing is something that we should explore in a lot more detail too. Like kind of the types of things that Mary Grace was talking about were super interesting.
Yeah, maybe this is a nice time we switch to the CSL proposal discussion. It's more forward looking. So I can quickly share with you my slides. So this is supposed to be informal, and please stop me if you have any questions. So I will quickly do a very brief introduction about the CSL proposal, and the upcoming one will be for November 1st this year to October 31st, 2024. And the due date is in late August, but I need to double check that. And based on the current machine situation, looks like the allocation might be partly on Shenyang and partly on Derecho. Again, we don't know that right now. And usually the proposal will be divided into more development-oriented or production-oriented. And here, give you an example. So that's the Paleo Working Group proposed simulation. And we proposed 28.9 million in development proposal and 26 million in production. And the CESM project had 623 million. And here is a select of the proposed community simulations in this past CSL proposal. So including the high resolution paleoclimate simulation, which we are working on right now, and the perturbed parameter ensemble, we are also working on that. So we proposed 10 million cal-hour for that. And also the LGM simulation using the high top atmosphere is done, and we are in the process of publishing the data. And the Henrik 11 meltwater event using CESM2 is also done. And Ryan led a small allocation performing a Pliocene simulation using ICSM 1.2. So this is just some example to give you an idea what could be in the CSL proposal. And there are some requirements, and we suggest that for people who want to submit community simulations in this proposal, it's best that you can lead the development, running, and the publishing of the simulation. Of course, the NCAR Paleo group is willing to help, but for some of the simulations, we may not have the capacity to lead the simulation. And for this proposed simulation, you should be able to contribute to the writing of the proposal, and then later the interim and final accomplishment reports when needed. And the proposed simulation should not be something in your NSF proposal or other agency-funded project. Should be more community-oriented. And it is required that you share the simulation boundary condition, initial condition files, and output with the community after the run is finished and the paper documenting the simulation are submitted. So for the details, you can check out this document listed here. Next, let's talk about some ideas about what kind of simulation you think are of high community value, and either yourself can lead, or some Paleo group at NCAR should take the lead of the simulation. Okay, I can stop sharing.
Hey, John. Oh, Betty had her hand raised. You can go first.
I was just going to comment that CESM2 does not have water isotopes in all the component models, and we're not clear what CESM3 is going to have. So just think about that. But CESM 1.2, 1.3 does. So.
Alex?
Sure. Sorry, I didn't raise my hand. So in talking with Bronwyn here at WashU, who's more on the paleoclimate data side, having certain types of transient simulations that go through certain time periods, like either a glacial to interglacial type of transient run, or like I saw you said the Paleo group is looking at a Holocene transient run with newer versions of the model, I think are really valued by people doing like leaf wax analysis and hydroclimate reconstructions to look at kind of, these changes through time. So I don't know if that's, necessarily something more that we would be doing here at WashU or NCAR would have a lead on, but I just wanted to mention that the data community is definitely interested in those types of simulations.
Okay, thank you. Clay?
Yeah, I just had kind of a quick comment on the potentially getting some type of intermediate water isotope version in CESM2, and maybe maybe it's more work than I think it is. But I seem like, so obviously the land model is out, but the ocean model hasn't changed too much. If we could get a version, and potentially I or some other people in our lab could help test some of this, but using, the CAM6 physics, I think would be interesting if we could pull over POP, and then whether we need to update with the estuary box model, that could be a bit of a challenge, but that would be something I'd be interested in seeing and possibly helping out with. Thanks.
Yeah, great. Thank you. I just want to add a few comments regarding Clay's points. I think if we have some intermediate version of ICESM, especially when we use CAM6, we can take advantage of some of the new capability of CAM6. For example, regional refined simulation and some new physical processes in the atmosphere model. I think that's a great idea.
Yeah, just to expand on that, it's the land model that I don't think we have any hope of, unless we can come up with a simpler, bucket model or something. We've discussed this with Jesse, but so far it hasn't moved forward. So that would be great. If Clay, for example, or others want to kind of brainstorm with us. But so far, yeah, it's the land model more than anything. CAM6 has it, but they haven't been tested.
Yeah, I think so. There's just follow up on that real quick. The paper by Rich Fiorella and others, they had a somewhat more sophisticated bucket model for the land. I don't know if that needs more testing, but that might be at least a holdover, allow us to do some stuff.
Okay, maybe Fanny and then Sam.
Hi, do you hear me?
Yeah.
Okay, so just to mention that I would be interested really on the high resolution simulation, but I don't know which time period you're considering or what, what would that be? Or you mentioned you're already working on it.
Okay, I can try to answer your question. So in RAN and make risk presentation, you already say that they are working on high resolution Pliocene simulation.
Mm-hmm.
And we have a separate project in which we propose to do high resolution, so roughly a 1/4 degree atmosphere and a 1/10 degree ocean, high resolution simulation of Pliocene, so this time fully coupled, and early Eocene, as well as the last glacial maximum. And we may consider to add a mid-Holocene if we have the computing resources.
Great, thanks for the info.
Okay. Maybe Sam and then Pedro.
Okay, sure. Yeah, I guess I'm not sure if this is a comment or a question or both, but it follows nicely from what Fanny was just saying. I'm really interested in the high resolution aspect as well, because I think that that's really necessary for doing more detailed comparisons of models and proxies. And so I guess I was curious as to whether the high resolution simulations that are already planned are going to be isotope enabled, and if not, I would suggest maybe doing some transient high resolution simulations of more recent periods, including isotope enabled capacity. And that's something that my group could probably contribute to as well.
So more recent periods, do you mean like last millennium or some specific?
Yeah, last millennium, mid-Holocene, early Holocene,
okay,
like that kind of epoch.
Yeah,
we have
right now,
sorry?
Mm-hmm. Right now, we can only afford to run the coupled simulation for several decades, maybe 50 years.
Sure, but maybe we could think strategically about how to select time periods that are relevant across the community, so not just for like Pliocene, Eocene time periods, but also maybe more recent as well.
Okay.
Can I add to that, Jean?
Sure, go ahead.
Besides the just how long you could run, the cost is very expensive on duration. You know, like, so it depends on what allocation we're given from the chief scientist, Gokhan. We figure 50 years at that resolution will cost 10 million core hours on durations. So maybe they'll give us a lot of time, but I agree with you, it would be great. I should also comment, we patterned these after the IHESP, so they do have an historical, not with isotopes, and a future scenario run that we could take advantage of. But I agree, we need to be proactive, and maybe there's other computing systems like the University of Texas, if we have an NSF grant where we could, I know they ported it to that computer. So the IHESP version, it won't have isotopes, but we can ponder if we can do that. So.
Okay, Pedro.
Yeah, I have two questions. One related to that. I was thinking, is anyone thinking of doing simulations of with volcanic forcing with higher resolution? Those are probably feasible with a few decades worth of computer time. And I think there's so much evidence that high resolution matters in the mid latitudes for Earth's interactions over western boundary currents. And those are the things that maybe think of a high latitude volcano with a tropical volcano, something a bit not idealized, but still maybe pave the way to one day do high-res simulations of the last millennium. And so that's one comment. And I'm happy to continue elaborating on this if everyone thinks it's a good idea. Question about CSM3. Since it has MOM as an ocean model, is there going to be a chance to start experimenting with that version of the model during Paleo soon? What do you guys know about that?
I can give you some update. So right now, they are testing the fully coupled CESM 2.x. So this X means you have Chem6 and MOM6. So right now they just started to test the coupled simulation in a modern climate configuration. I think when their exploration is in a better stage, we can certainly start to work with them to perform some paleoclimate simulation. And they are very open to this idea about testing the model more frequently, the coupled simulation more frequently using 4 times CO2 as well as the last glacial maximum.
So we might not be able to run an LGM simulation with that ocean model in the next year or through the next cycle of this proposal. Maybe wait for the next cycle.
I would say maybe it's challenging to get it done within this year. And because like you mentioned, we have a completely new ocean model, MOM6, and we don't have much experience setting up paleoclimate simulation using this new ocean model.
Sounds good. I think there's a lot of new science that could be done with that model, given that it represents coastal processes so much better than deep water formation over shells and all that stuff. Could be a priority. But we can always wait.
Yeah, I guess it might be possible in year 2. I think a concern is we don't know what their resolution is going to be and whether they're going to support a lower resolution. Again, it's a people matters. So it may be something we want to think about in terms of development, maybe in year or two, if people are willing to step up and work on that. What do you think, Jean? You think so? Okay.
Yeah, thanks.
So what type of resolutions are they thinking about? So we will, are you saying we will lose the 3-degree resolution, Betty?
You know, right now they're talking about 2/3 of a degree for the ocean. Mm-hmm. Yes, and higher top and higher top atmosphere, more levels in the ocean. And then I hear Frank show even higher. That said, I know there's quite a bit of support from the community to have maybe a 2-degree ocean, maybe not a 3-degree, but a 2-degree. And maybe with, performance, I'm not sure duratio is going to be processor faster, but it's going to have more and maybe work on that by the software engineers, maybe. So I agree with you, because if you want to do things like freshwater forcing, it'd be exciting to use MOM also. But maybe you need to go to the ocean model working group meetings and push that. Maybe we should have recorded
I'm always pushing for keeping the lower resolution versions of the models. Yeah. Also, the simpler models group, it's not a working group, but it's concerned about losing the lower res. I wonder if we should write a proposal to NSF just to maybe get someone to work on that.
Yeah, you know NSF better than we do. I mean, the Paleo group cannot submit to the Paleo program at NSF. Okay. Just at least Dave Gerardo will not. But and my sense is, talking to the model developers, it's hard to get money for model development, but with a good science emphasis, I don't see why you couldn't. And so I agree. I think it'd be great to do.
If anyone is interested on this, maybe we should talk. I'll be happy to identify a few science questions and for MOM6 and maybe try to get money to get an over res ocean.
Maybe I can add a related comment. The new workhouse configuration of CESM 2.x or CESM 3 will be quite expensive. It could be 10-20 times more expensive than the 2-degree we are using. Yeah, just to say that there's really community value if someone can lead a proposal to NSF and to work on this relatively causal resolution and a cheaper model. That would be great.
Okay, we should talk about this. I think it's a real issue.
Okay, maybe next Sam and then Clay.
Sure, yeah, I guess I was pondering kind of similar things, and I wonder if there's an opportunity here. I'm not sure which version of the model I'm talking about exactly, maybe CESM 2 or 3, but like if we can think about constructing perturbed physics simulations in paleo contexts that would correspond to things that we expect might be at least pre-production versions of the new models, to see if there's emergent behaviors that correspond to 21st century simulations. And maybe we can kind of get ahead of the inevitable development cycle where paleo kind of gets put to the side by thinking about likely parameters that are under development now, and pick those for some of the strategic time slice experiments, which I think relates to what Pedro was saying, but it would depend on the science question.
Yeah, thanks for the comment. We are currently working on a perturbed parameter ensemble in this paleoclimate context, and it is closely related to your point about try to inform the model parameters.
So I'm just thinking for the CSL proposal, you're doing that for CAM. Maybe it makes sense to, and I know they have one for the land, to, maybe include that in the next proposal. I don't know if it's possible, maybe Esther or Jean, to do the same for the ocean, or does it make sense with MOM?
I mean, I know there's a lot of choices that you can make in terms of ocean mixing parameterizations in both POP and MOM. So we could certainly think about that as targets, or maybe aspects of ocean biogeochemistry even that probably matter a lot for like climate variability.
Yeah, I don't know. I haven't heard of any talk of such an effort in MOM, and kind of sounds a little scary to me, actually. Knowing the oceanographers involved. So, but I mean, never say never, I guess. But I haven't heard of them at all talking about this. I mean, there was a talk, but not relative to MOM, by Laura Zana on using machine learning to look at ocean parameterizations. And she was one of our speakers on the first day, one of the speakers highlighted. So that's all I've heard about in terms of using new ways to identify the best mixing parameterizations for the ocean.
So about the next step, we are thinking about maybe we develop a short survey to send to the community, and the people then can respond to the survey regarding what you think should be included in the CSL proposal, and are there simulations you want to lead, so we can get a more formal feedback. Does that sound good?
Thank you, Jean. It'd also be useful if you and Ren and Samantha, or one of you, try to find out from GoCon about what maybe he doesn't know yet, but it's really hard to plan what to do unless you know. And I should say, in the past, he tells us what our allocation is, and then we fit what we can fit in it. So, the high res would be great, not just for last millennium, but for deeper time, but yeah, I just don't know what he's going to give us. So it'd be great if you could, if he has any idea yet, and maybe he doesn't, because Derecho keeps getting postponed in terms of its delivery and then release to the community. So now it's January. It was supposed to be, I think, March or April, I want to say. So, but that would be really useful if he knows that now, or has any indication. So.
Yeah, thanks, Betty, for the suggestion. And another information could also be very helpful is the model cost, especially if we are looking at the CAM6 with a higher model vertical resolution with the new MOM6 will be much more expensive.
I guess the other question I had is, are there any progress on like developing faster spin-ups? I remember ocean model, well, obviously we are all tied to the ocean model spin-up for any of the deep time paleo or even quaternary simulations. So I recall back in the days hearing like a lot of talks about like accelerated spin-up for the ocean model. So is there any development on MOM? And perhaps that's something we could try as well.
Keith Lindsay is working on that. And I don't think that can be immediately available for us, maybe in next 1 or 2 years. I'm not sure about the update.
You know, I think the key, yeah, I agree with Jean. I think the key is what you and Mary Grace did, and we plan with our ASD on Duratio, is you run at lower resolution. And you can run a lot longer at FV2x1, and you get the ocean to a state, and then you switch to higher resolution. So Jean, is the FV2x1 of ICSM 1.2 about 50 years per day now?
Yeah, 50
on
years.
Cheyenne. Yeah, so you can get, 2,000 years in a little over a month, probably. So it is doable now, but yeah, even faster would be great. I agree. But
yeah, I was mainly worried about, John mentioned the new model like CESM3 is going to be 20 times more expensive. And based on our past experience, if the ocean model is the one, is the reason that we have to run the simulation for a long time to reach equilibrium, perhaps we need to think about there are some intermediate ways we can spin up ocean faster.
Esther?
I just wanted to say that Keith's Newton-Krylov solver is only works right now for passive tracers, not for like temperature and salinity, which are the dynamic density, go into computing the density in the ocean model. So, and I'm not even sure they work for all of the passive tracers currently, but he's been using it to spin up the carbon pools in the ocean VGC, which take a really long time to come to equilibrium. So
we should query him, because I thought he was thinking of temperature and salinity, but don't quote me on that. I thought he was, but it's harder problem. So
I think it's a harder problem. And I think I've seen in his list, he wants to make it more user-friendly. So I think that maybe is his first target currently. So, well, anyway.
He did give a seminar on it back in, I don't know, February or March, so we could go watch that and see what he's saying these days. All the CGD seminars are posted online, so we could find it.
I'd be interested in trying it out.
There we go.
There's a user-friendly version.
I'll look for the link and send it to. But I think we're supposed to be in. Other people might want to go to the next working groups now. So
yeah.
But
okay, maybe we adjourn now. Thank you very much, everyone, for joining.
Thanks, everybody. This was interesting.
Thanks, everybody. Great talks. Yeah, see you guys.
Bye. Thanks.
Bye.